Okay, thanks. Let me share my screen. And yesterday we were talking about surface data sets and the importance of particularly soil data sets and uncertainty in the data sets. And I thought one person that we've worked with for a long time would actually know the answer to these questions of what is a good soil data set and how to bring those into the model. And that's Johan Fedema. But unfortunately, what we learned yesterday that after a long battle illness, Johan's no longer with us. And so I wanted to take a few minutes to talk about Johan and his many contributions to CLM. He was a affiliate scientist at NCAR. He was a longtime contributor to CLM and a visitor to the terrestrial sciences section. And I can say personally, he was a very good friend of mine, particularly in the early days of CLM. He was in development of that. He was somebody you could just talk to about science, about life in general, and just have a lot of fun conversations with. So what I wanted to do is just go over a few of his science highlights to remind everybody, if we think about the capabilities of CLM, a lot of these originate with Johan. And one of them is land cover change. We had a great talk yesterday about land cover change and land use in CLM and how to represent future land use and land cover change. Well, Johan was really a pioneer in that. In this 2005 paper in Science, this was one of the first papers to talk about the importance of including land cover change in climate projections over the 21st century. Johan was principally a data set person. He loved the data sets and developing them and the nuances of them. And we talk a lot today about uncertainty in our models. Well, Johan himself was already dealing with uncertainty over 15 years ago, particularly with surface data sets. And in this paper, he was talking about the importance of representing the present day land cover and different depictions of that and how that affected the model response to land cover change. So he was a pioneer also in this idea of uncertainty before really uncertainty became the hot topic. We also heard about the urban model in CLM. Johan, again, was the pioneer behind that. This is a paper with Keith, me, and Johan, also Mariana when she was the programmer for the land model, in developing an urban model for CLM. That has led to a lot of science in the model. This was the very first instance of an urban model in a global climate model, and I think that created a whole new frontier, whole new sort of science pathway. I don't think Keith would be offended if I said that Johan was really the brains behind our operation. Their collaboration, it continues today. This is a more recent article about data sets for the urban model. Again, data sets were Johan's passion. And it's really incredible to think that in a global climate model, we are now dealing with things like wall heat capacity or wall thickness or roof albedo and roof emissivity. Johan, the insulative properties of walls and roofs. Johan tracked all these things down and was able to bring in them in a very meaningful and realistic way into the urban model. Then the last thing I want to point out is, Johan, again, data sets were his passion. That's what he loved to work with, and think about how these data sets could be used to improve climate models and climate simulations. And he was working on a soil degradation data set. And so what I want people to remember is Johan was a really intellectual force behind the development of CLM. I think if the history of CLM is ever written, Johan will feature very prominently in that. And so as you think about the capabilities of the model, think about Johan, because he was behind a lot of what we have in our model today. And I will stop sharing and leave it at that.
Thank you, Gordon. Yes, we're all very sad to hear the news about Johan, and we appreciate this tribute to highlighting how important he is and has been in the CLM community. Okay, well, with that, we should probably transition over to some of the talks for this session. So first, we will have Cesar Dionisio Jimenez Rodriguez talking to us about the role of interspecific variability on plant hydraulic traits, or of hydraulic traits, sorry, in modeling plant water use strategies. So Cesar, if you are here.
Hi, how are you?
Hi, great. If you would like to share your screen.
Okay.
And Adriana will help time your presentation so that you have a sense for where you're at.
Yeah, I'll give you a 12-minute warning.
Okay, perfect. I'm trying to keep it under 10 because I'm really interested on the questions and discussions part.
Great.
So you are able to see my screen?
No, not at all. Doesn't look like you've actually shared.
Sure. It is not allowing me to share the screen, but I already sent the.
Yeah, it looks like the permissions are enabled for you to be able to share, so I'm not sure what's going on, but I'm wondering, Elizabeth, do you have the slides? Because we can just share the slides for Cesar.
I do. I just need one moment.
Okay. Yeah, this is why it's helpful that we have the slides. So thanks. So Cesar, when Elizabeth is able to start sharing your screens, just, I guess,
Okay.
Tell her when you would like the slides to advance. All right, it looks like we see them now, so.
Okay, perfect. So good morning, everybody. I'm Cesar Jimenez Rodriguez. I work on the Luxembourg Institute of Science and Technology. So for all the people in Europe, for us, it's already afternoon coming the evening. So our project is focusing on the using CLM to test the effect of droughts in Europe. So this talk we are speaking specifically of two PFTs, two type of land covers using that are in Europe. So next one, please. Can you go for the next slide, please? Okay. When we speak about the intraspecific variability of plant hydraulic traits, we see that on the forest we have different a matrix of different species that have different ages. With it come in different responses to water stress. You can click, please. And then when we see for the same species or the same genus, we can we can observe how this variability in species owns different responses to stress, to water stress. Even within the same species, you can click again, please. Within the same species, we can see how different organs on the plants, they respond differently to these water stresses. So as examples here, Picea avis or Pseudotsuga menziesi, for the different organs of the same tree, they have different responses to hydraulic stress. So click, please. One important thing here is how this wide variability in the vulnerability to hydraulic failure can be is affecting the model response, in this case through the use of CLM. The next one, please. So our our work here we have been focusing in point-scale simulations in different sites in Europe. And we are using, in this case, the capacity of CLM to compare the information provided for these experimental sites and compare the capacity to ingest this variability in hydraulic failure for different tree species. In this case, we are choosing Fagus sylvatica, that is a species, click please, widely distributed in Europe, and characterizing the broadleaf deciduous tree PFT. And also, we are using Quercus, that is an evergreen tree species located on the Mediterranean basin, and allow us to compare two different PFTs in Europe that they have different physiological responses, but also characterize trees growing under specific climatic conditions. Click, please. So under this, we were working in 4 different sites: Spain, in Spain, Puchavon and Hesse in France, and Ginese in Germany. But for this talk, we are presenting the results for the 2 sites in France. Hesse, that is, it has an oceanic climate, and then it has evenly distributed precipitation, and Puchavon, where the precipitation during the summer period is reduced significantly, and then allows the trees to provide a different response. Also, these sites were selected from the SAT-FluxNet dataset because provide us information on with a long time window and with a wide range of trees to provide a good estimate of the SAT flow. Next one, please. To characterize the vulnerability of these 2 species, we surfed through the silent functional traits, and what we did was to take all the information related to the to the vulnerability to water stress using the percent loss of conductivity, and we determine the values for the vulnerability curve that we need in CLM for a resistant tree and for a vulnerable tree. We can see that for Fagus sylvatica, this range, the difference between a vulnerable and resistant tree is more narrow than the one for Quercus. So with these configurations, we ingest these configurations into the model, and then we compare the different degrees of vulnerability of the response from the model for these 2 sites. Something important to stress here is that for both PFTs on the default configuration of CLM, they have exactly the same parametrization in terms of vulnerability curve. Here we are speaking about the P50, the CK, and the maximum conductance. Next slide, please. So we are showing 3 experiments. So for the first one, we have here on the right hand side the equation that governs the vulnerability within CLM. So for the first experiment, we ingested the P50 and the shape parameter for both types of trees, resistant and vulnerable configuration. Click, please. For the second experiment, we change the 3 parameters, the shape of the curve, and also the maximum segment conductance to characterize 2 extremes in terms of plant conductance. But something important is that because the link between the Kmax provided in CLM is not that easy to extract from the available data of the different species, what we did was to choose these values with 2 orders of magnitude of difference. I will show this later on. Next one, please. And the final experiment, we test the response to gradual changes of only the maximum segment conductance. Click, please, next one. So for the first experiment, here we are showing the response of the changing the shape of the vulnerability curve for Fagus sylvatica. Just to keep in mind that this one is a deciduous tree. So something important is that for the 3 configurations, the default configuration, the resistant and vulnerable configuration, there are no differences on the transpiration response that we get here. But there is an important thing to see that the resistant tree transpire more than the vulnerable tree all over the year. And this is something important to highlight because for the beginning of the year, the response should be exactly the same, but it should differ during summer because a vulnerable tree should should have a less transpiration response than the resistant tree. Click, please. And here, we can see the differences in how the different configurations affect the vulnerability during summer for this species. Next one, please. When we go to a drier place, as we have here with Quercus, we have an interesting issue, and is that the observed transpiration in this case is better represented by the vulnerable tree configuration. So this gives us an indication that for Quercus in this site, the changing the shape of the curve allows us to represent much better this type of forest. But there is a counterintuitive response when we have the resistant tree configuration, because a resistant configuration should transpire more than the vulnerable during summer. And in this case, the resistant configuration is being affected during the summer period. Click, please. And this can be seen on the response in terms of vulnerability. Next one, please. So when we combine the changes on the vulnerable curve with the maximum conductance, we can see important differences. Click, please. In how the changing these 3 parameters at the same time with choosing a vulnerable configuration, trees that they have a larger vessels to mobilize more water, we can have expected hydraulic failure during summer for the vulnerable configuration. Click. Meanwhile, the combination of resistant configuration and Kmax produces a leaf stress during summer, but allows the silent to do not experience water stress. We can see it here. Next one, please. So now, when we start changing
You're at 12 minutes, Cesar.
Perfect. This is almost the last one. When we change the Kmax, we can see how effectively we can induce a water use strategy on the trees. When we move from a larger Kmax to a smaller Kmax into the resistant, we can see how the response. You can see the 4 set of plots on the right. It has a better representation, having less stress. The final one, please. So next one. So here we have the take-home messages, and is that the representation of vulnerable and resistant trees requires a coherent selection of the three plant hydraulic parameters and not changing only the P50, because this one can create a counterintuitive response when we are working water-limited sites. And the most important from our side is that the maximum conductivity can be used to impose a plant water use strategy in the model. Thank you.
Thank you, Cesar. Very interesting talk. Can we, or I guess I'll open the floor for questions if anyone has questions. Give just a minute.
Go ahead.
Yeah, Will has his hand up.
It's Cesar, that was a really nice talk. I didn't catch at the beginning. Was that a SP run or a BGC run?
Excuse me?
Was that a configuration of the model using satellite phonology, so SP, or with BGC? With biogeochemistry?
Satellite
phonology,
information.
Okay.
Yeah.
Okay, great. Thanks.
Yes, Jackie has her hand up as well.
Thanks for that really nice talk. And so I think it would be interesting to connect and look at this in FATES. And so within FATES, we have FATES Hydro. It would be good to do this comparison, doing these site level tests with the two different species. I think it would be a powerful comparison with the big leaf version that you used, and then with FATES, which also has size structure. And so it adds a layer of complexity, but it might add more information in terms of the reality. And something I noted at the beginning of your talk, it seemed like the, and I can't remember which species, but even if you were looking at the resistant versus the vulnerable, the tree on the left of your slide, I can't remember which one, it seemed like it would still fit inside the range of resistance and vulnerability for the tree on the right. And so did you do any simulations sort of sampling in a real world situation in terms of competitive dynamics and survivability? Do you think you could classify these trees as one being overall resistant and one being overall vulnerable? And I understand that they have different responses, but from the database, it looked like one was just generally more resistant and then one was generally more vulnerable.
We are working that actually, that is the idea of the project. What we saw is that Fagus sylvatica, the representation given by the default configuration of CLM actually matches nicely the information that we have from Hesse. Meanwhile, for Quercus ilex, the configuration ingested, changing only P50 give us the wrong results, and we were not able to give one kind of classification. But when we start changing the maximum conductivity, we saw that it helps to classify more like an intermediate vulnerable tree without changing the P50, but only the capacity to transport water.
Thanks. Yeah, very interesting, but we should probably move on. So,
okay.
Thank you.
Yeah, thank you, Cesar. People, if anybody has additional questions, you can add them to the chat. And Cesar, keep an eye on the chat. So next we'll have Lei Zhao talking about understanding local urban climate change at a large scale using CESM and CLM urban.
Okay, thank you.
So Lei, yes, we can see your screen.
Okay, great. Thank you, Danica. All right, hello everyone, and good morning. And I'm very glad to be here virtually to present a few urban modeling efforts that's in my group. And so before I start, I really want to thank my collaborators and my students, especially my collaborators at NCAR, Keith, Bill, Peter, and Dave, and they give tremendous help and support to the research of my group. And actually, NCAR have given me tremendous help since the beginning of my PhD, actually a long time ago. And also, I want to thank Gordon for the lovely words for Yuhang. So although I didn't get a chance to work with Yuhang for a long time, we mostly communicate virtually and a few in-person meetings, but I know how wonderful a person and a colleague he is. I think all of the work that I will present in a second cannot happen without Yuhang. All right, so I will start with why we care about urban, why we are interested in urban. So I think cities are very unique and very interesting, as there's a very disproportionate mismatch between the city's area size and its impacts. So although only 2 to 3% of the Earth's land surface, but it houses more than half of the world population. And the urban population will continue to grow. The percentage will continue to grow to about 70% in roughly 3 decades. And a lot of the hazards like heat wave or water scarcity, air pollution and energy insecurity are either rooted in or exacerbated by the unique urban environment, unique urban dynamics, and those risks are expected to worsen in the future because of the rapid urban development and coupled with climate change. And I'm sure that a lot of you have seen these types of projections a number of many times. So this is typical global climate projections, especially surface climate projections under different scenarios, emission scenarios, and in multi-model or multi-ensemble projections. However, because of the small area size of cities, actually almost all of the state-of-the-art global scale Earth system models do not have a physically based urban representation and parameterization. So this type of global surface projections actually are essentially the global non-urban surface climate. And as we know that the urban has its own unique climate compared to surrounding or compared to the background climate, for example, urban heat island. So this traditional non-urban climate projection might not be able to really capture the urban signal. So then we are interested in a question that can we also provide as multi-model robust urban projections like this, but just for urban specific signal. And luckily we have CESM. So CESM has a physics-based urban parameterization and representation, and like what Gordon mentioned, based on their work with Liuhang Keith. And so this is a physically based urban parameterization in CLM or CTSM, and there are a lot of validation studies based on CESM against validation studies of CESM urban modeling against surface or tower observations across the globe. Here, I just show one example of the kind of the comparison between evaluation between model CESM model. This is it's an early version of CLM, so it's a CLM3, but you can see it's already did a good job. And we also there are many of this type of observational based validation. So I just select one here, and we also did our own validation, based on PRISM data sets. So here we showed 10 metropolitan areas across the US, and we compared the CLM simulation, CLMU simulation with WRF and the PRISM observational based data sets. And here is a map showing, and this figure is the WRF simulation, high resolution simulation, I think 4 kilometer. And we aggregated into the CESM one resolution grid cell and to compare with CLM simulation. And you can see the difference, which shows its bottom parts. The difference is very small. So give us the confidence of the CESM urban modeling. And then to produce that, produce the multi-model urban projection, so we develop a method that we want to combine the CESM, process-based CESM urban modeling with the physics-guided machine learning. And then we want to develop a kind of a reduced order urban climate emulator so that it can be computationally efficient and we can provide global scale projections of local urban climates. So essentially, this is basic. Instead of using the forcing data produced from the CAM to drive the CLM, we using the exact same forcing that CLM take, but to develop a machine learning model and to have the urban response. Okay, so the framework is like, so we use the CESM urban model to develop physics-guided machine learning regressor, and then so come up with an urban emulator, and then we can apply this emulator to other CMIP models which do not have urban representation, so that we can provide multi-model projections. And here I just want to quickly show the emulator accuracy. So we actually test this emulator on never seen data for a number of variables. Here I just show temperature, and you can see here is your RMSE. It's far smaller than the difference of different simulation ensembles. And we test, basically we can train, for example, we can train the emulator based on several CESM simulations and then test on other ensemble member simulations. And this is some results. And here, this is very quick, so we can show that the traditional CMIP multi-model projections cannot really capture the urban warming signals. And also you can see the urban, although there's a universal type of urban heat island effects, but you can see this kind of misrepresentation is not universal, right? There's no, you cannot just add a premium or a constant to the traditional multi-model projection to represent urban. And here I showed the final robust projections on urban warming. I'm not sure whether it's clear on the screen, but actually it's similar like the traditional multi-model projections of non-urban climate. We produce not only just the warming, but also the confidence or the inter-model robustness or agreement of each grid cell. So you can see not only how much temperature will warm in the future for the global cities, but also how confident different models agree on each other. And here is the humidity variable that we noticed almost universal, or actually, so most of the inland cities, we see a drying or a decreasing RH, a relative humidity trend. Most of the inland city, because you can clearly see the coastal line, the coastal cities actually, because the ample water supply, so we didn't see a large drop, but the inland cities, we see a kind of continuous dropping of the relative humidity. This is also actually consistent with some recent observational studies and also modeling studies. Okay, so we also actually have projections and discussions on human perceived heat stress variables in the paper, but for the time's sake, I will just skip that part. And in general, those are all the mean state climate projections. But how about urban climate extremes? And this is another project that my student did. And actually, this is my former student because he just started his ASP postdoc in UNCAR just last month. So yeah, and so my former student did this project. We applied this method into daily archive of the simulations. Want to see some extremes. So here we showed that the multi-model projections of urban heat waves, and you can see it's actually getting severe in 4 dimensions: intensity, frequency, duration, and total days. And in addition to these projections, we also want to understand the uncertainty. And as we know that, the multi-model or multi-ensemble multi-member projections, it has the internal variability, structural uncertainty, parameter or parametric uncertainty, and the scenario uncertainty. And on the time horizon of multiple decades or longer, actually the structural and scenario uncertainty dominate. So we want to understand how the structural variability versus internal variability contribute to the extreme projections. So in this project, we leverage also the large ensemble simulation of CESM, and with our emulated multimodal projections, so we can see how the structural variability and internal variability contribute to urban extreme projections. And here you can see along all the dimensions, actually the structural variability contributes more than half of the variability. So this is again showing that relying on one model to project urban future climates is probably questionable. So to further demonstrate this idea, we borrowed actually a concept of from tropical cyclone types of studies. So we call it gray swan heat wave. So we show that a seemingly unlikely urban heat wave events, for example, 0.01% probability projected using one model. But if we check their probability likelihood of multi-model, it's way larger. So it shows again the critical importance of multi-model.
You're at 12 minutes, Lei.
Okay, thank you. I will be very fast. And multi-model projections. All right. So another project is about urban climate building energy interactions, and we know that there are studies about biogeochemical feedback of warmer climate and energy use. And there are another sets of the feedback, which is about physical feedback, which is relatively harder to characterize, especially over large scales. But luckily, we have CRMU, so we leverage the most recent development by Kiss and Yuhang, the most recent updated urban building energy model, and we can investigate and study the dynamic interaction between climate and energy. And here are some projections about air conditioning and heating. And you can see the curvature and the uncertainty spread out compared to urban temperature projections. So to put it in the map, you can see that the temperature change actually translates to a largely spatial variant and a less robust AC demand change, and the dynamic interaction plays an important role in there. And for the time's sake, I won't talk too much details in this, and this is still ongoing work. And the last part of my presentation is a recent effort that we are doing, collaborating with NCAR, which is we want to implement a dynamic urban scheme into CESM. And so all of the previous slides that I showed are actually fixed urban. So the urban doesn't grow in the future, but we know it's not real. That urban we will have a rapid urban expansion in the future under different scenarios. And to put it into map, you can see the urban growth is actually prominent in a number of places across the world. And then currently in the CTSM, actually the global dynamic vegetation model and crop model, they represent a transient land use change. And to my understanding, the glacier part is also dynamic. And I think the lake part is also in development for the dynamic part. So that leaves urban the last piece of a static one. So we want to implement a dynamic urban CTSM. Actually, most of the model development work has been done already. So we have the issue here. If you're interested, you can follow our issue. And we already issued the PR, so it's merged with the master. So the function is there, and the ongoing work we are trying to improve a mixed surface data map tool and potentially this tool for user supplied urban growth data. So if you have your own, if you're unhappy with our default data sets, if you are happy, if you want to use your own future urban projections, and you can use the new tools to set up your own simulation consistent with multiple SSPs. So with that, I want to conclude the presentation, and thank you very much for being here, and I'm happy to answer any questions and comments. Thank you.
Thank you, Lei. I think we have to move on because we're right at the 15-minute mark, but I see that you already have 2 questions in the chat. So if you want to take a look at those questions in the chat, and respond to those. And if anybody else has questions in the chat,
Sure.
please do respond. And we also have time for discussion at the very end of today's meeting. So we can come back to some of these questions as well. The next talk is by Chris Still, and Chris will be talking to us about canopy temperatures in a warming world and looking at whether models capture the observed dynamics. So we'll give you the 12-minute warning, right, Chris? Go ahead and share your screen.
Okay, thanks. Can you see that?
Yep. It's not your, it's the slide view though. There you go.
Okay. All right, thanks. Thanks to the organizers. It's been a really stimulating workshop so far. And I'd like to acknowledge my co-author, Lenny Hawkins, who's a postdoc working with me at Oregon State University, and various collaborators shown here at the bottom. And as Danica mentioned, I want to talk about canopy temperatures and the observations we have, some new observations, and also how well models do or don't do in capturing the observed dynamics. Leaf temperature or canopy temperature, I'm going to use these sort of interchangeably. It's central to most land atmosphere exchanges, energy, water, and carbon. And the relationship is often really nonlinear. And just to give you a couple of examples here to help motivate this, I'm going to turn on my laser pointer. This is the photosynthetic rate for a summary across different plant types, C3 type plants. C4 type plants, we see a classic temperature optimum, and then it declines with higher or lower temperatures in a nonlinear fashion. Leaf respiration, like many types of respiration, with temperature as well. Like I'm competing with someone's baby. So there's a really an exponential increase in leaf respiration with temperature. And then finally, transpiration, as shown here on the right, increases, in this case, up to a maximum and then declines for a couple different plant types. But transpiration can increase monotonically or plateau. There's a bunch of relationships with temperature, but again, they're typically nonlinear. And just to help motivate this a little more, to show an example of what happens in a leaf level model if you use air temperature versus leaf temperature, what I have here is observations for daytime only at Harvard Forest for paper birch, one of the common trees in the Harvard Forest. And the open symbols are air temperature, and then the filled symbols, and they're filled by the incoming solar radiation or photosynthetic active radiation, are the filled, and those represent the leaf temperatures of paper birch across a series of days in the growing season. And what I've done here is I've taken a leaf level photosynthesis and transpiration model, and I've basically fed it with either air temperature, assuming leaves are at air temperature, or fed it with the observed leaf temperatures and looked at the difference. So for photosynthesis, for example, you can see the difference here across time in the photosynthetic rate is fairly substantial if you use leaf versus air. So it's leaf minus air, so higher photosynthetic rates when using the observed leaf versus assuming the leaf is at air temperature. For transpiration, this is the difference in the model as well through time. And the difference is for photosynthesis are up to 15% higher. For transpiration, it can be up to 40% higher when you use a leaf temperature that's observed versus assuming the leaf is at air temperature. So again, a really important role for temperature in models and in measurements. And again, on average, there may be a 3 to 5 to 7 degrees Celsius difference is a typical difference we see. A quick primer on leaf temperature. It's a product of the leaf energy balance. This just, excuse me, this slide just briefly shows there's the net radiation, the absorbed short and long wave radiation. There's emitted long wave radiation as a function of the well-known stuff on Boltzmann law. And then that absorbed radiation is partitioned into sensible and latent heating. And the storage term is typically ignored for leaves because it's usually quite small. And just to give you an example of how this works out in the leaf during daytime and nighttime, these are typical two-sided values for, in this case, absorbed shortwave radiation in watts per square meter, and then absorbed long wave, and then emitted long wave radiation. So those form the net radiation sort of available to the leaf, and that net radiation is then expended as sensible heating, in this case 190 watts per square meter, and latent heating of 180 watts per square meter. So the leaf temperature that sort of balances that energy budget gives you a value of 25 C when the air temperature is 20 C. So the delta here is 5 C, or very similar to what I showed previously at Harvard Forest. We see similar things at night. Leaves are not necessarily the same as air temperature. They're typically cooler at night than the air, especially on clear nights. On cloudy nights, they tend to be much closer to air temperature. But in this example, it's a couple degrees cooler than the air temperature. And so from the steady state energy balance equation, which is what I showed previously, you can basically write this equation for leaf temperature, and something like this is embedded in all the land models I'm aware of that try to calculate some version of leaf or canopy or vegetation temperature. So it's the air temperature plus this departure term, which is a function of the net radiation, minus the latent heat divided by a conductance to heat, basically. And so these terms can drive leaves warmer than air or colder than air. They can be colder than air during the day if the latent heating is really substantial, but typically they're a fair bit warmer than air during the daytime. So this is the basis for how models generally calculate the leaf temperature. And many of these same processes are influenced by basically canopy temperature. So really what I'm talking about here is more canopy temperature. Everything so far has been sort of leaves in isolation, but really what we think about in the models and what matters in reality is the temperature of assemblages or groups of leaves in the canopy. And we're calling that canopy temperature. So again, I'll use canopy and leaf temperature sort of interchangeably on the slides, but really I'm thinking mostly about canopy temperature. And you see the same processes here, the carbon fluxes, the heat energy fluxes, and the water fluxes, and the influence of the radiation. Okay, so getting to comparisons, there aren't many, and I have not done an exhaustive, deep dive into the literature. I've talked to a number of modelers about this, and they typically don't compare the predictions of models of leaf or canopy or vegetation temperature, whatever it's called, in the models against observations. There are some exceptions. This is one here that Jennifer Holm and colleagues worked on in the Amazon. There are different seasons here from their summer season to our winter season across time. Observations are in blue, and these are from leaf thermocouples, where we put little wires pressed up against leaves and measure the temperature of a whole bunch of leaves in a canopy. And then this is a CLM predictions, and I'm not sure which version of CLM this is, but it was a while back, actually. And the main thing to see here is there's a fair amount of dynamism in the observed leaf temperatures, even in a place in the Amazon. A lot more variation in the observations of leaf temperature than the model gets. The model tends to sit right at the middle between about 26 and 32 or 33, whereas the observations vary quite a bit, actually, at any given point. So in this case, the model was really underrepresenting the variation. And then that plays through in calculations of things like, for this paper, they were looking at leaf isoprene, which is also nonlinearly related to temperature. So this bias plays out in the model predictions. We have new ways of looking at canopy temperature, however, and that's kind of what I want to focus on for the rest of the talk, using canopy thermal imaging, using thermal cameras that you put on UAVs or aircraft, or in the case I'm going to talk about here, on towers, on covariance towers, and you mount a camera and it measures long-wave radiation coming off of the surfaces, and using a few corrections, it then solves for what the surface of that leaf or the canopy bark or whatever must have been to give you that long-wave radiation using the stuff on Boltzmann relationship. These cameras are really robust. You can park them on these towers in enclosures for years, and they can take canopy temperature pictures at high resolution for a long time period. They're quite accurate. They agree pretty well with leaf thermocouples, which have been the gold standard for temperature measurements up to this point. This is at a site at Harvard, and this is at a conifer tree in Oregon. They do quite well. And we now have a data set of a range of sites across the Americas. It's the largest of its kind in the world, to my knowledge, that can be used for a whole bunch of things, but including especially to look at model predictions. And this is an example of the Matolia, Ameriflux site in Oregon. This is the temperature map here. We have other observations at different sites along the West Coast at Conifer and other sites. We also have a site at Niwot Ridge that has thermal data, and then Harvard Forest, and then down at BCI. So what happens if you actually compare this data set, these sorts of thermal data, against models? Going back to the Matolia site, the Ponderosa Pine site in Oregon that I mentioned, this is showing the observations here in the dotted line. So a typical diurnal cycle where the canopy is colder than air at night and then warmer than air during the day, not by as much as, say, the paper birch I showed at the beginning, but still 3 degrees Celsius. That's the mean daily cycle across the growing season. And these lines here, these different lines here basically represent model predictions from a multi-layer canopy model, the SPA model that Matt Williams developed a long time ago, and then people have worked on since then. And each of the models represents a different assumption about what is being optimized, or different stomatal models like the Ballberry, the Medlin model. We also implemented hydraulics in this model, including the Sperry gain risk model. And the bottom line is all the models are drastically underrepresenting variation in the temperature of the canopy at this particular site. And I'll talk later in what that actually means for model predictions of things like transpiration. Just one more example of model versus measurement comparisons. This is at the Old Growth Wind River Forest in Washington. This is the ED 2.1 3D canopy model, and the observations are in black in the top panel, and the model predictions are in blue. This is just the upper canopy elements that we've captured with thermal imaging compared to the upper canopy elements in the model. And in general, you see that the model in this case actually overestimates the range in temperatures quite a bit compared to the observations. So counter to the previous 2 examples I showed. Because this is a 3D canopy, we can also look at, and at this site we had a camera on a pan-tilt unit, so we could look up and down on the canopy. This is the gradient in space from the top to the bottom. Observations again in black, model in blue, and the model both over and underestimates, but generally does a better job at capturing spatial variability compared to temporal variability. Okay, so what does this actually mean in models? Going back to the Matolia site, these are plots that Linnea has produced for a paper in review. The left-hand column is basically showing a scatter plot that represents what I showed previously, where there's a bias in the model that in the morning, the model is predicting warmer temperatures compared to the observations on the x-axis, and then in the afternoon, it's predicting colder temperatures compared to the observations, and that bias persists throughout the growing season. It has different implications, however, for the model transpiration. So in this case, the y-axis is model transpiration, including the model calculation of canopy temperature, so it's all internally consistent. And on this axis, it's transpiration, where Lin has basically forced the model to use the observed values of canopy temperature as opposed to its own calculations. And in the spring, it leads to more transpiration in the morning and less transpiration in the afternoon, the bias. Throughout the day, it more or less averages out, but any given time point, it's 5 or 10% off. And in late summer, it's the opposite. The morning warm bias in the model leads to less transpiration, and the afternoon cool bias leads to more transpiration. So important implications for model predictions of, for example, transpiration. There's lots of other things you could look at as well, but that's the one we focused on in this paper. Okay, this is my final data slide here, and this is basically, this figure is from Bharat Rastogi, and this is basically, the data are published in this paper here, again, this new phytologist paper, where we look at canopy temperature data. And what this is a series of scatter plots comparing the canopy temperature that we actually have from the thermal camera data. This is at the Wind River site in Washington I showed previously. So canopy temperature plotted against air temperature, or plotted against other metrics of canopy temperature that can be derived from eddy covariance data. So even at sites where we don't have these thermal cameras, which are most eddy covariance sites do not have these, there's other metrics of canopy temperature that can be used and compared against models. So the aerodynamic temperature, which is derived from the sensible heat flux, compares favorably well with the canopy temperature from thermal cameras. There's also an ability to estimate the bulk canopy scale temperature from the upwelling long wave, because all these eddy covariance sites have 4-channel night radiometers and they're measuring upwelling long wave. That also at this site compares favorably. And there's also satellite data. So the canopy temperature at this site from the thermal cameras compares favorably with the MODIS land surface temperature. So again, lots of different ways to get a temperature of the land surface for comparisons and testing models against these various observations. Okay, so this is my concluding slide. Just to re-summarize, it seems like from the not a comprehensive survey, but what I've looked at, the models are not really capturing the variability in leaf or canopy or vegetation in time or even necessarily in space. There's an opportunity, I think, to do more comprehensive testing of model predictions of temperature, which then again play out throughout other parts of the model, using thermal camera observations and also other estimates of canopy temperature from eddy covariance data sets. So again, I think I'd just like to have sort of like a call to arms to really focus on temperature of canopies in models because they're so critical to so many things. Okay, there's my timer. I think I'm at 12 minutes now. So thank you, and I'd love to take any questions. And thanks for your time.
Thank you, Chris. I see that Joshua has his hand up, so we can start with Joshua.
So two-part. One, you mentioned very briefly BVOCs. Do you feel that BVOCs are negligible in terms of heat exchange in the canopy? And the second thing is, can variation in leaf temperature, are you able to detect variation in leaf temperature with transpiration, under conditions where there is water limitation and plants might be changing their level of transpiration in response to environmental variables?
Yeah, good question. Yeah. So the first one, I don't know. I would guess it's negligible, but it's not something we've calculated or thought much about, to be honest with you. So it seems like an open question. I wouldn't think so, but not certain about it. Are you thinking about just the evaporative cooling from the BVOC emissions, or? Yeah,
there was. I know there was in the past. I heard that there was some controversy about whether isoprenes and terpenes actually were cooling agents, either not necessarily evolved, but they were actually in certain circumstances cooling leaves. But it was a matter of controversy, and I haven't followed that for some years, so I didn't know if the community had come to a conclusion on that matter or not.
Okay, yeah, I'm not sure. I guess the other question, you definitely could see transpiration variations. It depends somewhat on the type of canopy you're looking at. Big broadleaf canopies, I think it's more obvious the difference that's imposed by transpiration. Canopies like this one here in the photo, the ponderosa pine, they tend to be pretty coupled to the atmosphere, so you don't see as much of an effect of transpiration, I think, in the variations in the temperature in systems like that. So I think it depends so much on the leaf type and then the canopy structure. But you definitely see it. And you probably know this already, but thermal imaging really got its start in agricultural applications to look at this exact question. And that definitely works very well for that.
Thank you, Chris. Gordon has his hand up.
Yeah, I'll just make this quick. Chris, great talk. I love the work you've been doing on leaf and canopy temperature. I think it's so important.
Thank you.
But I had a comment about like the SPA model. As I remember it, it actually doesn't do turbulence above and within the canopy. The air temperature at each level in the canopy is the same air temperature as at the forcing height, so the tower reference height. So it's multi-layer and radiative transfer, but not in sort of air properties, temperature and wind speed and things like that within the canopy. And so I was wondering how much that might sort of be affecting the biases you were seeing, when you compared the simulated versus observed temperatures.
Yeah, absolutely, Gordon. Yeah, thank you. And I think Linnea, who did the simulations, is on the call, and she can chime in. That is definitely the direction we're going to try to diagnose what's going on with the model and why it's underestimating. And I guess that also illustrates why these temperature data are useful to sort of point you to look at these things. Having said all that, at the Matolia site, at least, we did look at the observed, there's vertical air temperature data at that site to see if there's observed variations in air temperature. And at that particular site, again, because it's pretty well coupled, there's not much of a gradient in air temperature. But again, that doesn't mean we're actually calculating the turbulence at multiple levels in the model. So yeah, it's a great observation though. Thank you.
Yeah, thanks, Chris. I think we need to move on, but there are a few questions for you in the chat as well, and any additional questions can be in the chat. So if you can stop sharing your screen,
yep.
That would be great. Yeah, and TC, if you want to share your screen. So our next talk is by TC Chakraborty, and looking at diffuse radiation fertilization. So yeah, you can unmute yourself. Get started.
Hi, can you, sorry. Can you hear me?
We can hear you, yeah, and we can see your slides.
Okay. Hello, everyone, and good morning. I'm TC. I finished my PhD from Yale University last year and joined the Pacific Northwest National Lab as a research scientist soon afterwards. And today I will be giving you an overview of some of the work I've been doing as part of my PhD on the diffuse radiation fertilization effect, and also kind of some follow-up research that I'm currently working on. So the diffuse radiation fertilization effect is the phenomenon where due to the presence of scattering agents in the atmosphere like clouds and aerosols, the direction of sunlight basically changes, which we call diffuse radiation. And because of this change in the incident energy, normally shaded leaves can now take part in photosynthesis, which means there is carbon assimilation as well as transpiration from the canopy, enhanced transpiration from the canopy. So there has been a lot of observational evidence of the diffuse radiation fertilization effect. However, it is hard to get global estimates from observations because of the lack of simultaneous measurements of diffuse radiation and the surface energy and carbon fluxes. For instance, in the figure to the left, these are all the Emery flux and FluxNet towers with those simultaneous observations. And you can see that none of them are in the tropical region, where this effect is going to be most, generally strongest. However, for the stations for which we do have the data, we do see some evidence of the fertilization effect. Basically, we divide the latent heat flux data and the gross primary productivity data into bins of absorbed shortwave for the site, and then further divide that into a high and a low diffuse fraction regime. So high being greater than 0.65, low being less than 0.35. And we see that in all of these shortwave bins, we do see higher latent heat flux and higher gross primary productivity for the high diffuse fraction regime. This is for one FluxNet site with the most data, but we see similar results for most of the other sites. So during my PhD, part of my work was focused on understanding how aerosols affect the surface energy budget. And this happens both due to the global dimming effect, so the reduction in total shortwave due to aerosols, as well as the diffuse fertilization effect, where aerosols are increasing the diffuse radiation. Due to the lack of observations, I used a modeling framework, which started with generating forcing fields from CAM version 6, and then running that with radiation diagnostics to remove the effect of all aerosols. So basically all forcing data are same except for direct beam radiation, diffuse radiation, and long wave radiation, which is not as important here. And then, so these are the polluted case and the clean case. And then the final case, I kept the aerosol radiative effect the same, but then fixed the diffuse fraction to be the same as the clean case. So now you can, using like the equation to the right, you can separate out the effect of global dimming and diffuse radiation fertilization on any variable. So I looked at all the subcomponents of evapotranspiration. This includes total evaporation, and then divided into evaporation from ground, canopy, transpiration from sunlit leaves, and transpiration from shaded leaves. Here I'm showing the results for all land grids as well as for the tropical region. I have results from the other climate zones as well. And so CLM internally partitions the total transpiration into sunlit leaves and shaded leaves, which I basically output for this work. And here you see the changes in the subcomponents of evapotranspiration due to aerosols. So a few things to note here. First, the solid bar is the net effect. This includes the global dimming effect and the diffuse radiation fertilization effect. Then the hatched bar is the dimming effect, and then the blank, empty bars are the diffuse radiation fertilization effect. Overall, there is some compensation between the global dimming effect and the diffuse radiation fertilization effect. So there is a overall reduction in latent heat flux, and the effect of diffuse radiation fertilization is much lower than the effect of global dimming. However, if you look only at the transpiration from shaded leaves, you see that there is a net increase in the transpiration due to the higher impact of the diffuse radiation fertilization effect on that component. Similar to the evapotranspiration, I also looked at the subcomponents of the carbon budget. Here, the interesting difference from latent heat flux is that there is actually a net increase in gross primary productivity due to aerosols, even though I am actually reducing the total energy reaching the terrestrial surface. This is because the diffuse radiation fertilization effect, as modeled by CLM, is more important than the global dimming effect due to aerosols. So you can see that again for global case and for the tropical case. Now, there are a lot of uncertainties with these estimates, one of which relate to the diffuse radiation forcing itself. So I did evaluate the CAM radiation forcing fields against the global energy balance archive sites. This shows the distribution of all the sites, the figure to the right. And although the overall variability is captured well, CAM underestimates the diffuse radiation and overestimates the total shortwave radiation. So by like roughly 10 watt per meter square in either direction. So in a separate study, I also compared these observations from GEBA with several current generation, mostly reanalysis products, which publicly archive diffuse radiation. So this includes NOAA series DOE, ENSOP-NCAR, MERA2, ERA5, and the Sirius satellite product. And what you see is that there are large differences both between the products as well as against the observations given by the black bar here. And I'm showing here the seasonality of the northern hemisphere grids. And especially you can see for like the summer months, if you move from MERA2 to Sirius, you're seeing an almost doubling of the diffuse radiation. So my question was, given that there is this much uncertainty in the diffuse radiation forcing, what would that mean for gross primary productivity and latent heat flux? So recently, I basically ran CLM with BGC for 100 years with the same forcing for meteorology, but only the diffuse radiation and direct beam radiation varied based on the 6 products. So that's the 4 reanalysis series and the CAM climatology. And in all cases, this diffuse fraction is adjusted based on monthly values, so that the total shortwave is actually the same for all cases. Only the partitioning between the diffuse radiation and direct beam radiation vary. So in the first figure to the left, you see the standard deviation of the gross primary productivity across these 6 model runs. And you can see larger standard deviation in tropical regions like Southeast Asia, Congo Basin, even like Eastern China. And the marked regions here show regions where the coefficient of variation, that's just the mean by standard deviation, is less than 3%. So if it's less than 3%, all the models are relatively strongly in kind of agreement regarding the numbers. And this is done because standard deviation is, of course, dependent on the baseline values, and they will be higher in the tropics. So it's hard to compare between the tropics and the polar region without some normalization. For latent heat flux, we similarly see higher standard deviation in like the Congo Basin, parts of Eastern China, but note that the coefficient of variation is within 3% in all cases. And this is in line with what we saw for the aerosol case, that diffuse radiation fertilization effect is more important for the gross primary productivity than for the transpiration. So in this plot, I am basically showing the global and tropical gross primary productivity for the 6 model runs versus the diffuse fraction. And generally, you see a pretty strong linear correlation with the diffuse fraction increasing, the gross primary productivity increasing with increases in diffuse fraction. And for the global case, we are basically moving from 114 petagrams of carbon per year GPP when using the MERA2 diffuse fraction to a 7% higher value of 122 petagrams of carbon per year when using series. This is not a, I guess, negligible difference. Like it's like half the standard deviation across models, and it's greater than the land carbon sink. And there have been studies talking about how the diffuse radiation fertilization effect is like one of the missing components for better constraining that land carbon sink. For tropical areas, we see a 9% difference when moving from MERA2 forcing to the to the series forcing. And then I did the same thing for latent heat flux. And again, we see a positive correlation, but the difference is less. So latent heat flux increases by roughly 1.1% for tropical grids when moving from MERA2 to series. And this is because there are compensating effects. So transpiration from shaded leaves actually increases, which makes sense. And transpiration from sunlit leaves goes down. And this is because the total incident energy is constrained in all of these model runs. Now, note that all of these results are from CLM, and that to the kind of the pseudo 2 big leaf version of CLM, which has the shade, like one shaded and one sunlit canopy. Different models taking part in the in CIMIP6 have very different canopy representation. A lot of them do pull from previous versions of CLM, but there are also others which have, for instance, multi-layer canopy, which have basically each layer responds separately to a different radiation forcing due to the canopy layer radiation budget. And then you have the one big leaf models which do not have a shaded leaf, so you are not explicitly considering the diffuse radiation fertilization effect. So it would be interesting to note how sensitive these different models are to this same range of forcing to figure out how important this mechanism might be to the kind of well-known variability in gross primary productivity across land models. So in summary, we see that even when the total incident radiation is kept constant, the diffuse radiation change can modulate gross primary productivity and the surface energy fluxes. This mechanism is hard to quantify using observations. So we turn to global gridded data sets, which also show large differences. So we use this realistic range of gridded diffuse fraction to force the latest version of CLM. And we note that there are large differences in gross primary productivity and less so for latent heat flux. So this kind of brings up the need to actively, systematically examine the simulated diffuse fraction in atmosphere components and the diffuse response in the land models across the MIP6 models. And as far as I know, in none of the current MIPS, that is a mechanism that is being considered. So anyway, thank you and happy to take questions.
Thank you, TC. We can open the floor up for any questions. Give people just a minute. It looks like Dave Lawrence has his hand raised.
Actually, why don't let Rosie go first?
Oh, Rosie has her hand raised too. Yeah, go ahead, Rosie.
Yeah, so thanks, that was really cool. In the Fates model, we have a multi-layer canopy. It doesn't have, for Chris, etc's benefit, it doesn't have multiple resolutions to temperature, but it does have multiple layers for radiation. And within that framework, we recently introduced the capability to change the thickness of the layers, and also to change how the thickness of the layers changes through the canopy, right? So before we had all the layers the same thickness, and now we can have thin layers at the top going to fat layers at the bottom. Thanks to Charlie. And so yeah, I'm really interested to know whether the representation of layering affects this field. Yeah, it would be pretty cool to see if we could do some experiments using the same kind of forcing data that you've put together. I personally am interested in doing that. So if you're interested, we could chat online.
Yeah, I am really interested, because I knew there was a multi-layer canopy, but I don't know. I think 2 years ago, I think I talked to Gordon, and he said it was not linked to hydrology at that point. But I guess I basically moved forward with the pseudo two big leaf version. But it would be good to see whether how the sensitivity basically changes. I know there was at least one paper which showed that the carbon response to diffuse radiation is overestimated in CLM. It was Kennedy et al. 2021. I don't know if that is improved in the multi-layer canopy version. So I would love to. I have all of the forcing data sets, so all the default forcing at global scale. So I can reach out to you. We can talk.
Great. Thank you.
Rosie, just to be clear, are you proposing a Fates SP?
I am.
Yeah. Yeah, I think it'd be good. Donica, you want? Yeah, go ahead.
Yeah, we just so that everybody knows that we're right at the 15-minute mark. So we can continue to ask questions, but it's going to eat into our break. So if you wanted to put questions in the chat, you can do that. If people wanted to stick for the next few minutes during the break, that would be great. But I think we should allow people the opportunity to take a break and come back at 10:25. We're a few minutes behind, so I think pushing it to 10:25 would be great. So Dave, TC and Dave and Gordon, if you still have questions and want to stick around, that would be great.
I'd like to hear Gordon's question.
Oh no, mine was more of a clarification. TC, is that the multi-layer canopy that I've been developing is different than what's actually in Fates. Fates is actually doing it for radiative transfer, and I guess it's tied to also photosynthesis and stomata conductance. Mine's more complete in that it also does leaf temperature as part of the photosynthesis and stomata conductance, and also does the aerodynamics within the canopy. And that sort of then relates to what Chris was talking about too, in the question I had raised for Chris. So there's sort of different meanings of a multi-layer canopy. Mine is the full complete one, but that is on the CLM side, and it requires really major coding of CLM to get it into CLM, whereas what Rosie's talking about is sort of photosynthesis and stomata conductance and radiative transfer on the Fate side of the model.
Thanks, Gordon. Yeah, yeah. I mean, so your version is still running for sites, then individual sites.
Yeah, mine only runs for individual sites because the real problem with it is that it's not tied into the hydrology and the soil temperature of CLM. So it can actually run within CLM. I've done that, but you then get into a different sort of hydrologic and thermal states because the CLM surface flux calculation is tied to the soil temperature calculation, which is also tied to the Yeah, to soil temperature and soil heat transfer. So you can't separate all those things. And so I can put my multi-layer canopy into CLM, but it doesn't conserve energy because CLM does something completely different with soil temperature, and it's not compatible. So I only can run it for very short time periods where energy conservation really isn't that important, like a few days or up to a month or something like that. I think Nancy actually had a comment. I saw something from Nancy in the chat. So why don't you go ahead and actually say what you're going to say now?
Sure. So when we were designing the canopy model for the GIS vegetation model, we actually tested out the effect of solving for the vertical layering and temperature in the canopy, and we found the fluxes were not that sensitive to variation through vertical variation in temperature of the canopy. So just so for computational efficiency, we opted not to bother to do that layering. We'll just do layering of light. And important to get sunlit versus shaded extinction through the canopy also. So you'll save your GCM, computational time if you find it's not significant, not worth that to compute.
I mean, so we're sort of getting into a general topic here for everybody, but something that really has come up with, I agree with you, Nancy. It's that light profile is the number one thing to get a hold of. There are some subtle differences in that, like the upper canopy, which is where the sunlit leaves are, or have higher wind speeds, and lower in the canopy where the leaves are more shaded, and that tends to become really important. But then the other thing I discovered in all this is that the upper canopy can get water stress during the day. When you put plant hydraulics in, the upper canopy can get stressed during the day. And so the stomata close, and then you get these really higher temperatures in the upper canopy. Then the lower canopy, it also sort of shifts where the photosynthesis is occurring deeper into the canopy. And that's something that I don't know if CLM with its it's a two big leaf canopy, sunlit and shaded leaves, but it has different sort of leaf water potentials for sunlit and shaded leaves. I don't know if CLM is really capturing that or not, because the sunlit and shaded portions of the canopy change during the day. So I don't know. But anyway, that's the thing I've really noticed with a big leaf multi-layer canopy versus a big leaf canopy, is the upper layers can get water stressed during the day.
Well, the upper layers also have saturation in the photosynthesis too, so that sort of compensates for if you don't capture the water stress. And in our canopy model, we do also have a numerical scheme for solving for the layering as depending on the light conditions, like extinction, so that solutions will converge. So the layering varies. That might be one approach. I don't know if Rosie wants to do that in her development.
I think that I would let Rosie speak for herself, but it's possible she went to take a break. But we should definitely circle back onto this when we have the discussion at 11:20. Because Gordon's work with the multi-layer canopy and then your work, I think it would be good to bring this together and talk about how we could do that on the FATE side.
And not only multi-layer, clumping.
Yeah. Yeah, but I would, I'm going to go take a short break, but I definitely want to talk more about this, and maybe today is the day. So
yeah, thanks. Yeah, please come back in 10:25.
Okay, I'm hoping that most people are back from the break. It is 10:25, and I'm also hoping that Claire is here. Hey, Claire.
Hi.
All right. Yeah, so let's get started again with our next set of talks. So Claire Zarakis will tell us about atmospheric feedbacks and how they mediate plant trait influence on land surface fluxes. So Claire, if you can share your screen and then unmute yourself and get started.
All right. Can you see that all right?
Yeah, we sure do.
Great, thanks. So hi, I'm Claire Zarakis. I'm a PhD student in atmospheric sciences at the University of Washington. And today I'll be talking about how interactions between land parameter uncertainty and the atmosphere are important when we're thinking about parameter uncertainty. So I'm interested in this topic because we know that parameter uncertainty is a really major driver of kind of overall uncertainty in our understanding of land surface fluxes and how the land responds to climate change. And secondly, we know that land surface perturbations can generate really substantial atmospheric responses, but there hasn't been much work combining these two areas, especially with modern Earth system models. So I'm looking at land parameter uncertainty in this coupled context. And today I'll be focusing on a single land surface parameter, the Medland slope, or G1. I'll kind of be using them interchangeably. And this parameter directly controls the leaf level coupling between carbon gain and water loss. So CLM represents stomatal conductance as a function of photosynthesis, vapor pressure deficit, and CO2 concentration. And this relationship, this functional form, depends on these two empirically fitted parameters, G0 and G1. So the G1 parameter here directly controls the exchange rate between carbon uptake and water loss. And I was interested in looking at model sensitivity to this parameter in particular, because there's kind of a biological basis for why this parameter should exert a strong control over water and carbon fluxes. And additionally, past work such as Katie Dagin's parameter uncertainty analysis found that G1 has a really large impact on water fluxes in CLM. So in the context of G1 in particular, I'm asking these two questions. First, how does the Medland slope or G1 influence the atmosphere? And secondly, how do atmospheric feedbacks modulate G1's influence on the Earth system? So to answer these questions, I ran both coupled and offline model experiments where I perturbed this Medland slope parameter. So I ran 3 coupled simulations in pre-industrial conditions, one where I set the Medland slope parameter for each PFT to a plausible high-end value based on an observational data set, default parameter, which is the mean of that same data set in CLM, and then a low-end parameter. And these were all BGC concentration-driven equilibrium experiments with the slab ocean. And then I took the coupler output from that default coupled experiment, and I used that to force the atmosphere for another set of offline model experiments. So these were configured in exactly the same way, except for the key difference that the atmosphere couldn't respond to land surface changes. So that coupling was broken. And I can isolate the impact of atmospheric feedbacks by comparing the model's sensitivity to the Medland slope in a coupled context to the model sensitivity to the Medland slope in an offline land-only context. So before getting into the atmospheric feedbacks, I want to take a minute to walk through kind of more fundamentally what land surface properties the Medland slope can actually affect. So we think of the atmosphere as responding to changes in evaporative resistance, albedo, and surface roughness. And these are all emergent properties of CLM, which the Medland slope can potentially impact. So most directly, G1 will influence evaporative resistance. So at the leaf level, we expect that a higher G1 is associated with higher stomatal conductance. So we'd have lower evaporative resistance of the land surface, and we'd expect more transpiration, all else being equal. And just as a sanity check, in the offline case, we see that increasing G1 from the minimum to the maximum does in fact increase stomatal conductance. So this is showing the difference in noon stomatal conductance between the high and low parameter perturbations. And because albedo is affected by things like leaf area, G1 also modifies land surface albedo, but in a more spatially variable way. So the Medland slope alters these land surface properties that influences land to atmosphere fluxes of water, energy, and momentum. And so I'm going to talk through how these atmospheric feedbacks modulate G1's influence on the Earth system by looking at these 4 variables which we care about. So temperature and relative humidity to look at G1's influence on kind of atmospheric state, and evapotranspiration and GPP to look at G1's influence on ecosystem function and water and carbon fluxes. So starting with temperature, these Medland slope experiments show that atmospheric responses amplify the extent to which the Medland slope can impact near surface temperature. So this left map is showing the parameter impact in the offline configuration. So there's a pretty small temperature change across most of the globe. And the right map is showing the temperature difference in the coupled model. And here temperature decreases pretty much everywhere by quite a bit. So about 2 degrees Celsius in many regions. So pretty significant. And the mechanism for the sign of change here is that increasing the Medland slope increases evapotranspiration, which decreases temperature. And I wanted to start with temperature because it isn't a surprise. So we already know that atmospheric feedbacks are super necessary for allowing land surface changes to drive temperature responses. So this amplifying effect is exactly what we'd expect. And Marisa Legou very cleanly demonstrated this with CESM previously with an idealized land surface model. In a similar vein, atmospheric responses also amplify G1's impact on relative humidity. So this is a zonal mean plot of G1's impact on relative humidity in Northern Hemisphere summer, with the offline parameter effect in the dashed line and the coupled parameter effect in the solid line. So increasing the Medland slope increases relative humidity, and when the atmosphere is allowed to respond, altering the Medland slope can change relative humidity by up to 8 to 10% in some latitudinal bands. So the first take-home point here is that the atmospheric state is really sensitive to the Medland slope and other land surface parameters. So uncertainty associated with these plant traits can propagate to further uncertainty associated with atmospheric quantities. So this isn't probably too much of a surprise for this community, since the climate can't change kind of by definition in an offline run, and the climate can change in a coupled run. But I think the interesting aspect is not the qualitative change so much as the kind of quantitative magnitude of these changes. So next, we can look at how these atmospheric changes feedback on surface fluxes, starting with evapotranspiration. This is another zonal mean plot, this time showing land latent heat flux in Northern Hemisphere summer. And this time, atmospheric responses reduce the Medland slope impacts, especially in the Northern Hemisphere high latitudes. So in an offline configuration, perturbing G1 yields a latent heat change that's about twice as big as the latent heat change we actually see in the coupled context. So this means that for evapotranspiration in this region in the summer, atmospheric feedbacks are stabilizing, so they're actually reducing the sensitivity of latent heat to this parameter. And this is because of relative humidity and cloud cover feedbacks. So the initial perturbation to the system is an increase in evapotranspiration due to increasing the Medlin slope. That increases the relative humidity, as I showed earlier. And that decreases atmospheric demand for moisture, which suppresses evapotranspiration. So it's a negative feedback that counteracts the effect of that initial land surface perturbation on evapotranspiration. Additionally, increasing the relative humidity increases cloud cover at these high latitudes, and that decreases the solar radiation reaching the land surface, which reduces the energy available to evaporate water. So that's another feedback which reduces the impact of the Medlin slope on evapotranspiration when looking at a global scale. So the second take-home point here is that atmospheric responses aren't always just positive feedbacks. They can be amplifying or dampening feedbacks on uncertainty, depending on the variable you're interested in. And I think this is important to recognize because and I think many people often think of adding the atmosphere as increasing uncertainty because it's increasing complexity. I think that's probably true in general, especially when looking at future changes, but in kind of some narrow questions, it could be a stabilizing influence. So lastly, I'll turn to GPP. And this is another example of a dampening feedback. So the Medlin slope can directly affect photosynthesis, and atmospheric responses to changing the Medlin slope can modulate that impact. And here, the largest difference between the coupled and the offline parameter effects occurs in the tropics, where atmospheric responses are dampening the impact of the Medlin slope on GPP. So we can look at that region in a little more detail. This is the seasonal cycle of GPP in the low and high experiments, averaged overall 20 south to 20 north. So the same G1 perturbations yield a smaller range in the coupled context than in the offline context. And that reduced range is mainly because atmospheric feedbacks decrease GPP in this low Medlin slope case. So the question is, why do we see that? What atmospheric response is reducing GPP in the coupled experiment compared to the offline experiment? And this map is showing the difference between these two blue lines spatially. And it looks like atmospheric feedbacks are having the biggest impact in the Amazon. So I have
you're at 12 minutes.
Okay, almost done. Thank you. Two hypotheses for why this happens. First, atmospheric responses increase Canopy BPD in the coupled case, which drives further stomatal closure. And secondly, atmospheric responses are increasing maximum temperatures, which could reduce photosynthetic capacity. So in the context of this particular parameter, we found that atmospheric feedbacks amplify land impacts on the atmosphere, but can dampen the impact of parameter uncertainty on ecosystem function. I don't think I can generalize that. So the next step for this broad parameter uncertainty question is to do this with a bunch of other land parameters that I've selected based on the offline parameter perturbation experiment. So if you're interested in that kind of question, definitely get in touch. It'd be great to collaborate, and I'd be happy to save any history variables that you're interested in. So happy to answer any questions. Thanks.
Thank you, Claire. Fascinating talk. I always love this model connected to parameters, how much they're changing things. So let's open the floor for questions for Claire. It looks like Dave has his hand up.
Yeah, nice talk, Claire. Did you look at variability? Like, did it change variability, intraannual variability?
Yeah, I looked at variability, and for the most part, the atmosphere increased variability, I think, in water fluxes, but decreased variability in the carbon cycle. But I only looked in the global mean. So I think the Amazon feedback was probably driving that, since there's a lot of Gpp there. But yeah, I think
I
that's
have
a
to
super
locally.
interesting aspect of the question.
Locally, or you could do zonal mean. Maybe.
Yeah. Thanks.
Gordon has a question.
Yeah, Claire, that was a great presentation, great work that you're doing. And this is a more general comment, but we can start with you, but then maybe other people can think about it too. It's what you're really showing is that feedbacks with the atmosphere are so important, and yet a lot of the model development and a lot of the work we do is uncoupled, forced with the particular meteorology. So we don't have those feedbacks. And so what does it mean when we learn something in an uncoupled model versus a coupled model? And how are we supposed to sort of deal with these differences between the two configurations? I don't know the answer to that at all. So I'm not expecting an answer from you. I just want to have a conversation about it,
Yeah, I think that's a really important question. And I also don't have an answer, but I'm interested in trying to get some more kind of unifying framework for how or when the atmosphere kind of dampens or amplifies the impact of parameters, because I think that would be helpful from a model development perspective, to the extent that you're tuning parameters to some extent based on the offline runs. If there are some cases in which we really expect the atmosphere to amplify or dampen the effect of that parameter on whatever you're tuning to, that I guess it also just kind of advocates for coupling to the atmosphere sooner in the model development process before you get too far along, because it could kind of spin out if you wait.
Yeah, thank you, Claire, for answering those questions. I think we need to move on, but if others have questions, please put them in the chat for Claire. And Claire, please pay attention to the chat and answer there.
Thanks.
Yeah, thank you. Can you stop sharing your screen as well?
Yep.
So next we have Wen Kong, who will be talking to us about understanding the responses of summer continental daily temperature variance to perturbations in the land surface evaporative resistance. So go ahead and share your screen.
Okay. Can you see my slide well?
Yes, we can see your slide. Thank you.
Okay, great. Okay, thanks for the opportunity for sharing my work here. My name is Wen Kong. I'm currently doing my postdoc research at UCLA. So this is a work I did in collaboration with my postdoc mentors, Karen McNeil from UCLA, Alex Simpson from NCAR, and also our collaborator, Maurice Legout from University of Saskatchewan. I'd also like to thank Dr. Gordon Bonin from NCAR for providing helpful comments and conversations during the early stage of this work. Okay, so we know that in order to get a complete picture of how temperature extremes would evolve in a changing climate, it is not sufficient to just consider changes in the mean temperature. We need to have a good understanding of how would the whole distribution change in response to climate forcings. So here I will be talking about an effort to improve our understanding of what drives the day-to-day variation of the near surface air temperature over land. I think for this audience, I don't have to spend too much time to convince you that it is not an easy task to get an accurate prediction of the temperature variance, especially at daily to synoptic timescales. And that's because the near surface air temperature, it sits at the interface between land and atmosphere, so it is strongly affected by processes from both sectors. So for instance, the temperature variance over land can be affected by the radiation imbalance and also circulation in the atmosphere, such as horizontal thermal advection or adiabatic compression from subsidence. It's also affected by the land surface conditions, such as how wet or how dry the land surface is and what type of vegetation cover that we have at the surface. And these land surface conditions are especially important in driving the partitioning of the latent heat flux and sensible heat flux. In this talk, I will focus on the impacts of the evaporative resistance on the summer daily temperature variance over land, and I will use RS to denote this land surface property in the rest of the talk. So just a brief introduction of RS, what it is and why should we care about its impacts. RS is a land surface property that controls how difficult it is for the evapotranspiration to occur at the land surface. In other words, it controls the water flux from land to the atmosphere. And the reason why such a control matters for temperature variation is that it can not only affect evaporative cooling, it also has the potential to alter the water vapor amount and cloudiness in the atmosphere, and therefore affect shortwave radiation reaching the surface. RS is also a function of vegetation types. For example, in general, forests have higher RS and the crop or grasslands have lower RS. So the problem that I want to address in this talk is that if we assume an idealized world where all the global land area is covered by forests, and if we convert the vegetation cover from forests to grass or croplands, and how would the summer temperature variance respond, and what physical processes lead to those responses? So to answer those questions, I'll be using an idealized land surface model called the Simple Land Interface Model, or SLAM. It was developed by Dr. Marissa Legout during her PhD study. So for audiences who are not familiar with the model, SLAM is a land surface model we can run within the CSM framework. The default land component in CSM is Clm, which is a very comprehensive land surface model which covers different land surface processes and geophysical and biogeochemical cycles. Like other complex land models, Clm represents our most updated understanding of what is happening in the real world. But the fact that all these processes are coupled together sometimes give us a hard time to assess the impacts of individual land surface properties. Compared to Clm, SLAM gave us grid control to separate the impacts of individual land surface properties. So the way it works is that in SLAM, we have a simple bucket model for hydrology, and we can prescribe all the essential surface properties, such as surface albedo, soil thermal properties, surface roughness, snow masking depth, etc. And what is really unique about SLAM is that we can just perturb one single land surface property without changing anything else. And here we perturb RS in SLAM, and we will see how it affects the temperature variance. Just a quick look of where does RS play its role in the model. This is the equation of the latent heat flux representation in the model. So essentially, latent heat flux can be controlled by the near surface humidity gradient, the aerodynamic resistance, and the evaporative resistance. Recall that this RS parameter is what we perturb. It's the only thing we perturb in the model. But I also highlight the beta factor here, which is a function of the water bucket fullness. And the beta factor matters because the ability for the land surface to evaporate is also affected by how much water is available in the bucket. So when the bucket is relatively full, beta is equal to 1. So in this case, we would expect that decreasing RS will simply give you an increase of latent heat flux. However, if decreasing RS removes too much soil water in the bucket, that may make the bucket relatively empty. In that case, beta will decrease, and that will introduce some additional resistance to the evaporation and act to counteract the impacts of decreasing RS. Okay, so here are some more technical details. We couple SLAM with CAM6, and we use prescribed SST. The simulations are integrated for 45 years, and we use the last 40 years for analysis. And during the rest of the talk, I will only show results from the summer, that is JJA for the Northern Hemisphere and DJF for the Southern Hemisphere. And we'll focus on the comparison between two idealized simulations where we prescribe uniform RS values over the global land area. One simulation has higher RS value at 1,000 seconds per meter, and the other case has smaller RS value with RS equals to 20 seconds per meter. And you can think of this as a way to mimic the impacts of a global scale deforestation on the day-to-day variation of summer temperature over land. All the other land surface properties are prescribed and kept the same between the two simulations. We derived these properties from the CESM fully coupled historical simulation, and I will skip those details here. However, I do want to show one boundary condition, which I think is important for us to understand the results we get. So that is the bucket depth. So the bucket depth tells us what is the maximum water the bucket can hold. So you would expect wetter regions have deeper bucket and the dry regions have a shallow bucket. So what I did was that I integrated soil water throughout the effective root zone depths to get the global pattern of bucket depths that we prescribe at each grid point. So it largely captures the spatial pattern of the wet and dry regions. So for instance, we give the wet Amazon region a deeper bucket and give the arid Western US a shallower bucket. We looked at the impacts of decreasing RS in SLIM from 3 angles. For the sake of time, I will focus on talking about changes in the summer daily temperature variance. But essentially, we saw a global scale surface cooling, and we saw that when we decrease RS in SLIM, the land atmosphere coupling becomes stronger, and the overall land surface was shifted toward a more water-limited regime. If we still have time in the Q&A session, I can talk more about these 2 aspects. So here we are looking at the fractional change in the variance of summer daily temperature anomalies in response to a reduction in RS. So as we can see, changes in the temperature variance are not spatially uniform, despite the fact that we imposed a uniform RS perturbation everywhere. And overall, we see an increase of temperature variance over mid-latitude region and a decrease of temperature variance over the tropical land and the polar region. So the question we want to ask is that what is the first order explanation for the temperature variance response to the reduction of RS in our simulations? To answer this question, we should ask ourselves which physical factors matter in controlling this temperature variance response in the context of our simulations. Recall that at the beginning of the presentation, I mentioned that temperature variance can be affected by different processes from land and atmosphere. Since we perturb RS, and it can affect the latent flux and potentially other surface energy fluxes, we will test whether we can understand the temperature variance response that we saw in the last slide from a surface energy budget perspective. So what we found is that perturbations in RS can directly alter 2 surface energy flux terms. As expected, it can affect the latent flux through changes in the evaporation efficiency and the potential constraints due to the beta factor in dry regions. It can also affect shortwave radiation at the surface because by changing the water flux from land to the atmosphere, decreasing RS also alters the cloudiness and the water vapor amount in the atmosphere. So we write the surface energy balance in daily anomaly terms in this way, and we view the left-hand side as the forcings of changes in the temperature variance in the context of our simulations. And we view the terms on the right-hand side as the response to the forcing. And we ask this question, can we understand changes in the temperature variance from changes in the combined variance of shortwave and latent heat flux? In other words, can we see a match between the changes in the variance of shortwave minus latent heat flux and the changes in the variance of temperature? Indeed, what we found out is that changes in the combined variance of shortwave minus latent heat flux present a coherent spatial distribution in comparison with changes in the temperature variance. And if we take values from each land grid box between these 2 maps and plot a joint PDF, this is what we get. As you can see, there's indeed a quasi-linear relationship between changes in the temperature variance and changes in the combined variance of shortwave minus latent heat flux. So it seems that the mystery is solved, but is this the whole story? As we can see, this is not a purely linear relationship. And although the spatial pattern of these 2 variance change are largely consistent with each other, there's also mismatch in terms of the sign of variance change in some regions. So I also explored whether horizontal thermal advection also played a role in driving the temperature variance change.
You're at 12 minutes.
Okay, almost there, thanks. So this map shows changes in the variance of near surface horizontal thermal advection. So as you can see, the changes in the thermal advection variance are noisier, but the change in the northern hemisphere largely resembles what we saw from changes in the temperature variance. And if we plot for each latitude, if we plot the correlation between changes in the temperature variance and changes in the combined variance of shortwave minus latency flux in this red curve, and we plot the correlation between changes in the temperature variance and changes in the advection variance in this blue curve, you can see that although in the southern hemisphere, it seems that changes in the shortwave minus latency flux variance dominance, but in the northern hemisphere made to high latitude, the impacts of the thermal advection cannot be ignored. Okay, so to summarize here, examine impacts of RS perturbations on summer daily temperature variance through idealized simulations. And what I found is that by thinking from a surface energy perspective, changes in the summer daily temperature variance over land can be largely understood from changes in the shortwave minus latency flux variance. However, that is not the whole story. We should not ignore the potential contribution from the thermal advection, especially over the northern hemisphere made to high latitude. So I'll stop here and feel free to contact me if you have any questions or ideas to discuss. And I also want to mention that I believe Marissa is currently collaborating with several other colleagues from NCAR trying to implement SLIM into the CSM framework so it can be more widely used. So please reach out to her if you have questions about model.
Thanks, Wenwen. I think we have a little bit of time for questions if anybody has them. Give folks a minute. I guess while we're waiting, I'll just mention that some of my work has shown that the seasonal cycle of latent heat flux can change due to crops where you actually have higher transpiration rates during the summer, during the peak growing season, but lower transpiration rates in the shoulder seasons. And so that can change the annual cycle, which I imagine will change the variability. I don't know if that's something that you've considered at all.
I guess so. So the simulation that I did here is even more idealized compared to what you mentioned. I think, yeah, that's a good point that seasonal cycle should be taken into account. But when we do this simulation, actually we did not consider the seasonal cycle.
Okay, thank you. Do we have time for the question in the chat, Adriana?
We should probably move on. So, but maybe you could answer that in the chat, and then we'll have time to come back to all of these after this last talk.
Okay.
Yeah. Yeah. Okay, that sounds great. Yeah. So if you want to answer that question in the chat, Wenwen. So the last presentation of our morning is a joint presentation with Daniel Kennedy, Katie Dagin, and Dave Lawrence on the CLM5 parameter perturbation experiment. All right, and Daniel, we can see your screen, so you should all be good to go. You'll need to unmute yourself to talk.
All right, great. Thanks everybody for sticking around. Just as a caveat, this is a kind of a 30-minute talk instead of 12, so buckle in.
Yeah, I'll warn you at maybe 25 minutes.
All right, sounds
to
good.
wrap up.
So I'll be talking about what we've been hinting at a lot all week, the CLM5 parameter perturbation experiment. There's been a lot of talk this week about parameters, a lot of different studies on this, so very exciting stuff. What we're working on is quantifying parametric uncertainty and working towards automated calibration. So I've been working with Katie and Dave on this, but also a much broader CLM5 PPE working group, which I'll discuss a bit as we go through. So our goals for the CLM5 parameter perturbation experiment is to carry out comprehensive parameter uncertainty assessment and calibration of the BGC version of CLM5. Katie, this is kind of a follow-up from Katie's work, did similar process, but for the satellite phonology version of CLM5. And along the way, we want to develop infrastructure for easier PPEs, parameter experiments, and automated parameter estimation, so that we can explore sensitivity of a range of features of the global land system to reasonable uncertainty in model parameter values. So the plot that I like to look at for this in terms of parametric uncertainty is the accumulated land flux over the historical time period and then out into the future to 2100 across a range of land surface models. So this is an older figure from CMIP5 showing that there's a wide disagreement among Earth system models on the strength of the land sink. You can see that the spread across the models is equivalent to about 100 years of current fossil fuel emissions. And, a majority of the models consider or are prognosing that the land will be a net sink through 2100, but there is a set of models, CLM being one of them, CLM4 here, that contend that the land will be a source of carbon through to 2100. This is a major disagreement and a major source of uncertainty for land surface modeling. So fast forward to CMIP6, the next generation of models do agree on the sign. So now all of these Earth system models in CMIP6 agree that the land will be a sink of carbon in the future or through to 2100. But the spread is roughly equivalent. So we have not really constrained our estimate of how strong the land sink will be into the future. And so one of the questions we're hoping to get at with this parameter perturbation experiment is how does a single model's parametric uncertainty compare to the multi-model spread? So that green model is CESM2 with CLM5. So if we vary all the parameters in CLM, does the kind of uncertainty cloud look relatively small, or does it look huge compared to the range of this set of Earth system models? And in that same vein, can we use a parameter perturbation experiment to automate model calibration? So take, for example, this as your target and you're thinking about historical carbon fluxes. Can we look at which parameterization of the model achieves the best fit to historical carbon fluxes in a more automated way? So that brings us to the CLM5 parameter perturbation experiment, BGC edition. So our objectives here are to discern parameter sensitivities across a range of processes, quantify parametric uncertainty, automate model calibration, and facilitate future PPEs with a generalizable workflow. So I'm going to start there and talk about some of the infrastructure we've been investing in to make parameter perturbation experiments easier, faster, and more repeatable. So the first kind of big investment here was identifying and extracting all CLM5 BGC parameters. There's approximately 200 parameters in CLM5, the BGC version. So this was a big effort by Katie Dagin, Keith Olson, and Sam Levis to identify all the parameters, move any hard-coded parameters to the param file, which makes them easier to manipulate. And then we also created some new parameters for things that we were interested in perturbing, like how sandy the soils are or how deep the bedrock is. The next step for infrastructure for our experiment was defining reasonable ranges for all of those parameter values. So no one person in this working group knows enough to fill out parameter ranges for all 200 parameters where, we've got plant hydraulics, we've got photosynthesis, we've got fire, we've got hydrology, allocation, nutrient cycling, all sorts of things in the model. And so we made this as a Google spreadsheet and tried to enlist domain experts to come in and fill in PFT ranges or fill in parameter ranges for all 200 parameters. All right, so the next step for infrastructure, excuse me, was taking those parameter ranges and actually creating an ensemble of simulations using that. So the general workflow for this is you have one base case that you clone a bunch of times for each parameterization. And I think, many of us have written our own scripts to accomplish this workflow. But what we're finding is that turning one base simulation into thousands is really very generalizable. And we're hoping to create a utility that can be shared so that people don't have to continuously rewrite the same workflow. So at this point, we have tools to generate parameter files, submit ensembles. We can even tether segments of simulations together if you want the spin up as a separate simulation. It works for one at a time or like Latin hypercube style. And for us, we found it easiest to kind of specify the parameters and the parameter ranges from a Google spreadsheet. So our workflow is able to read directly from that Google spreadsheet. At this point, you're still on your own for creating your base case, because that's the one part of this that really isn't generalizable. But I think that's kind of how we see things in the future. You create your base case, and then you could use this utility to turn it into, 500 parameter perturbations or something like that. The nice thing about this is it's generalizable. It would work at global, point, or regional scale. I think with a little work, we could make it generalizable across model components as well, and model versions, as long as we keep up with little changes with SEAM, which is the kind of software side of submitting simulations. And all of this is online on GitHub. Katie and I put a fair amount of effort into this and would love more people to use it and give us any feedback. All right, so then the next really important thing was cost management. So we're trying to run, thousands of simulations of a global model. Global simulations are expensive. 1 degree land only simulation features 21,000 grid cells, just land grid cells. A 2 degree simulation, you get about a quarter of that. So over 5,666 or over 5,000 grid cells. And the question here is how much extra information in terms of understanding parameter effects is provided by that like 5,666 grid cell, right? Not all of the grid cells are kind of equally informative. And our colleague Forrest Hoffman has shown that a small subset of grid cells can reasonably replicate global mean, standard deviation, and transient model output. And so Forrest and Nate worked with us and helped us test this kind of sparse grid idea. And we use the ILAM system to choose a number of grid cells that we thought could reasonably represent the globe for our experiments. And what we found is that with 400 grid cells, we could reasonably replicate kind of global dynamics. And that gives us a more than 10 times speed improvement, which is, very big for us in terms of being able to do these large ensembles of simulations. The other thing that's prohibitive with the BGC version of the model is spin-up. A standard spin-up takes like 2,400 years to get all of the carbon stocks into equilibrium. But Yichi and colleagues have developed a faster spin-up using their matrix approach, and that has provided us another 10x speed improvement. Without these kind of two innovations, I don't think this experiment would have been possible. But you're talking about maybe like our setup here is like 200 times faster than a standard 2 degree simulation. So from that, we're able to tackle this one at a time ensemble. So we're varying parameters, like any given parameter, like Medlin slope Claire was talking about. You pick a high value and a low value. So 200 parameters, get 400 simulations. We're running this in a control climate. So we have a 140-year spin up to get all the fluxes and stocks into equilibrium. And then another 10 years where we do our analysis. So the control simulation, CO2 is 367 ppm. And for spin up and the analysis, we're cycling meteorological reanalysis forcing from 2005 to 2014. So this experiment costs about 240,000 processor hours. And just for reference, the TSS allocation for a calendar year is about 40 million processor hours. So, this is a reasonably large experiment, but not huge in terms of our overall allocation. So why go for one at a time? Why vary the parameters one at a time? It yields an easy to interpret data set. Also, we know that many of our parameters will have kind of very small effects. And likewise, we can't really afford a Latin hypercube with 200 parameters. Latin hypercube meaning varying them all at once instead of one at a time. So this is kind of our first result from the one at a time ensemble. I'm plotting average annual GPP across the ensemble. So annual GPP is on the y-axis, and then each of the dots is one of our simulations with some random parameter perturbed. And what you'll notice, say, if I sort, instead of plotting these as a scatter plot, sort the, it's the same data. I'm just sorting the ensembles by GPP. You can see that about 2/3 of the perturbations have less than 1% effect on GPP. So most of them have a very small effect on GPP. And actually 8 of our parameters provided identical output to the default simulation, which pretty much means that those parameters were deprecated and no longer do anything in the current model. So this type of experiment helped us to figure out, which parameters we don't need to include in our Latin hypercube experiment, which will follow. So we started with that control simulation, but we were also interested in how the model, or how parameters affect the model response to things like CO2 fertilization, climate sensitivity, and nitrogen sensitivity. So we had 5 more experiments. There's one typo on here. This should be 867, but we kind of decided to separately perturb CO2 and then climate instead of doing kind of a pre-industrial experiment and a future experiment. So we have low CO2 and high CO2. We have a pre-industrial climate from 1850 to 1859, taken from the CESM large ensemble. The forcing is, and then a future climate from the end of the century. And then we also did a nitrogen deposition experiment where we have CO2 and meteorology from present day, but added 5 grams of nitrogen. So all of these experiments together are just a really rich data set that we hope a lot of people can use for any of their questions for parameter sensitivity in a one at a time framework. So just one example of kind of what you could look at from this experiment. So you could plot up the average annual cycle from these 6 different simulations. So the blue line here is our default parameterization, and then the gray shading shows the full spread of all, basically like 400 simulations. But I'll make that same point again, that most of the simulations don't really do much. So this is the full, the gray bar here is all of the simulations, the full ensemble range. And then there is a gray bar on each of these annual cycle plots, but that's plus or minus 1 standard deviation. So you can see that the spread among our one at a time ensemble members is very small in general. Likewise, we have done a lot of analysis at the biome level instead of those plots were global annual cycle. So these are histograms of ET, so evapotranspiration, in the control high CO2 and low CO2 simulations for different biomes. And what I'm roughly showing here is that the CO2 fertilization effect on ET varies quite a bit based on what biome you're looking at. So I'll pick up CO2 fertilization again here. I was interested in asking, how does the CO2 fertilization effect on GPP vary going from pre-industrial to present? So going from 285 to 367 ppm, as compared to 367 to 867, right? So that's the future CO2 fertilization, what we've got so far and what we can expect to achieve in the future. And so it looks like the default simulation has about 17% increased GPP for present compared to pre-industrial. And then on top of that, another like 50 to 53% heading towards the future. And then you can do add all of our other ensemble members, right? And the general trend here is if you had low fertilization up to today, you'll probably also have kind of low fertilization into the future, which is, an interesting result and one you probably expect. And then you can look at kind of what parameters get you onto the really high side of fertilization or the really low side. So if you have reduced K max, that's kind of like a plant that's really stressed out water-wise. Yeah, getting extra CO2 really helps. If you have a high Medlin intercept, that plant really doesn't have that much control over its transpiration because the baseline transpiration is high. So it doesn't have as big of a response to CO2 fertilization. So I'm trying to give kind of a rapid run through of some of the analyses that we think you can do with this data set. And then if this is kind of an invisible line showing that, the trend where CO2 fertilization in present relates to CO2 fertilization in future, it's interesting to look at kind of what parameters fall farthest from that line. So hopefully that gives you a taste of kind of the data that we have. All of the data is available on the NCAR supercomputer. There's over 400 parameter perturbations across those 6 forcing scenarios. We have daily, monthly, and PFT streams. And we actually have like a Jupyter notebook template for interacting with the data. It helps read in an ensemble. And I've written a bunch of helper functions with the help of Dave and Katie and others for the various analyses seen here. So startup costs on analyzing this is probably only like 15 or 20 minutes to get going, to get it up and running. And then you can do a lot of interesting analyses, especially if you're comfortable with the sort of like Python, Jupyter X-ray analysis environment. And likewise, if you do pull this stuff down and do any interesting analyses, please, submit a pull request and we would love to absorb any of your functions and collaborate on developing a library of functions for analyzing this sort of data. So the next step is doing a multi-factor ensemble. We want to understand how different parameters interact with each other because you can't really assume linearity. This is just a made-up example, but you can imagine that if you increase like the base flow kind of subsurface runoff parameter, maybe you would depress GPP by 10%. And if you make the soil sandier, that would also depress GPP by 10%. So if you put those together, you might expect, all right, 10%, 10%, something like 20% GPP when you combine those with each other, but maybe they amplify each other somehow. And you would get, when you combine the increased base flow and sandiness, to get GPP depressed by 40%. And so for good calibration and uncertainty quantification, it's really important to vary parameters all at once, such as through kind of the popular Latin hypercube sampling technique. But as I've shown, it's probably not necessary to include all 200 parameters. And we're, based on our computing, allocation, et cetera, we probably can't afford an experiment with all 200 parameters. More parameters you have, the more simulations you have to carry out. So that's where we're at now, which is trying to decide which are the most important parameters and trying to define a framework for reducing from 200 to down to 50 parameters. But there's a couple of caveats with this. One is you have to avoid a tropical bias. So here's just from the default model configuration, here's this is a map of how much of global GPP does each grid cell contribute, right? And so these bright yellow pixels are showing that the tropics tend to light up a lot and contribute the largest quantity of global GPP. And for example, broadleaf evergreen tropical trees, which is just one of our 16 PFTs, accounts for 25% of global GPP. And it's pretty much the same story for transpiration. Those trees actually account for 28% of global transpiration. So if you're picking model parameters based on global fluxes, you're really going to end up kind of oversampling tropical trees, assuming that, you know, for us, one of our interests is representing the whole globe well and all of the regions reasonably well. All right, so that was our first caveat, that we want to avoid a tropical bias. The second caveat is it's really important to survive spin-up. Some parameterizations that work reasonably well in the present day aren't going to work well in pre-industrial situations, and then they wouldn't survive spin-up, and those are actually non-viable parameterizations. So we want to survive spin-up and include any parameters that might not be super important for present day, but show themselves to be important for how the land responds to the future. So here's one example of that. I'm plotting annual GPP in the 2010 climate versus annual GPP in a warmer climate. And similar to that CO2 fertilization, if you had low GPP now, you're probably going to have low GPP in the future, you know, a very strong relationship there. But there's this one parameter that has, you know, a pretty small effect on present day GPP, but has a big effect on warm climate GPP. So you might be tempted, if you only considered present day climate and response, to ignore this variable, but it's actually really important for how GPP evolves in the future. So that's our second caveat: survive spin-up and make sure you're capturing the climate response. So parameter selection, it's not me, it's some algorithm, is the decisions are trying to decide on what are the 50 most important parameters. So we know that what kind of information streams are gonna feed into this decision algorithm. Definitely global annual mean for some things, global interannual variability. We also want to include responses to those different manipulations like CO2 climate and nitrogen deposition. And likewise, we're going to include some biome level information to avoid having a tropical bias. And what's also important for us is not to just use something like GPP, but to have this span multiple metrics like that hit the different domains of CLM, like LAI, snow, runoff, fire, etc. So the decisions are that algorithm, the basic workflow here or process is calculate parameter effect, sort and select for the most important parameters, repeat across a variety of metrics like GPP, LAI, etc. Repeat across all of our different biomes.
You have 5 minutes.
Okay, and then repeat across the various perturbations like CO2 climate and nitrogen deposition. So just parameter effect is just the high perturbation minus the low perturbation. So which parameters control, for example, 10 centimeter soil water? So if you look at global mean, it's mostly the hydrology parameters that pop up at the top of the list, and then a couple of plant parameters. But if you look at interannual variability, the plant parameters become a little bit more important. And then you see that soil evaporation and soil organic matter parameters pop up. If you look at the response to CO2 fertilization, it's all the plants, which makes sense, right? Even though it's a hydrology metric, soil moisture, how it changes in response to extra CO2 is mostly mediated by plant parameters. And then lastly, if you look at how soil moisture responds to a warmer climate, you have a couple of hydrology parameters, but then you actually have 3 plant acclimation parameters that pop up. So that makes a lot of sense. And so by looking at these different lists, we're going to end up hitting a few different kind of domains of the model. So that's mean, inter-inner variability, and 2 responses. We can also look at biome level analysis. So we've got 9 biomes. And so you would get kind of like your top 5 for each biome. And the main takeaway is that if you want to increase GPP in the tropics and the drylands, you're going to look at parameters that avoid water stress. But if you want to increase GPP in the extratropics, the parameters are going to be the ones that maximize light use efficiency. And so by doing a biome level screening of important parameters, we're going to hit both of those domains of the model, both water stress and light use efficiency. And so that brings us to the kind of tricky question of how many parameters overall and how many do you grab from each of those lists. So we decided to work backwards from 1 million processor hours. And so we have 305 years per simulation. Each simulation costs 4 hours per year, 4 processor hours per year, and then we need 15 simulations per parameter. So that gives you about 55 parameters. And you have 204 lists. So that kind of, you could say you don't have enough parameters, but what you'll notice is that there's a lot of duplication. And so we found that even if you take like top 3 from the globals and top 1 from the other stuff, you only end up with 48 parameters. And I'll show this link again at the end, but you can find the full list online. All right, so the last point I'm trying to make here is something that Katie found in her SP ensemble, which is that good model calibration requires regional levers. So Jmax B0 is a global parameter. It's a lunar parameter with strong control on Jmax. And what you notice is it's basically a kind of univariate increase in GPP. If you have plants, you're going to get more GPP when you increase Jmax B0. You don't get much regional specificity with this parameter perturbation. So we have several PFT level parameters where you can change a parameter just for a given PFT, one of our 16 natural vegetation PFTs. So here's the footprint of reducing Medland slope for broadleaf evergreen tropical trees, which has a clear regional signature across the tropics. But CLM has 16 natural vegetation PFTs. If we perturb them all at once, then we can't discern regional hydrology levers because the signals will be mixed together. And on the flip side, it'd be very costly to perturb them all independently. Medland slope would add like 16 params towards that 50. And what you'll notice is with this simulation, everywhere that's gray here, we're essentially rerunning the default simulation, which is kind of a waste of computing time. And so what we're looking for is, can we find like PFT pairings, where in this example, these are boreal shrubs. So I can run my tropical trees and my boreal shrubs at the same time, but because they're regionally distinct, I can still figure out who did what in terms of the hydrology. And what we're asking here is, how much more information can we get by grouping things into, the default is 1 parameter file, vary all of the Medland slopes, but what if we use 2 parameter files, 3 parameter files, etc. So this is kind of the last thing I'll show. Here I've got my 16 natural vegetation PFTs on the x-axis, and then our 9 biomes on the y-axis. And the color coding here is basically saying anywhere where it's dark gray, this PFT affects GPP in this biome, okay? So you can see this is pretty sparse at a 5% effect. So a 5% effect on GPP, dark grays in the same row, you probably wouldn't want to put them onto the same parameter file. But as long as I have 2 parameter files, I can split these up effectively. So for example, I could put these 4 PFTs onto param file 1 and these 3 PFTs on param file 2, and they shouldn't have any interaction with each other. And we should be able to kind of, after the fact, disentangle the response. And then we're planning to distribute the less impactful PFTs onto those 2 parameter files as well. And then I'll just
30 minutes.
Yeah, this is it. Thanks, Adriana. And so we could do 2 param files, or maybe we want to do 3. And so what I'm showing here is that kind of the next threshold for GPP is 3%. Then you start getting 3 of these dark gray boxes per row. So from there, we're going to start our Latin hypercube experiment soon, within the next month or so. And then stay tuned, but this is kind of our big thing we're thinking about now. Is the output from that is very interesting and exciting, but it's definitely going to require some more sophisticated techniques for analysis and trying to figure out how to best leverage machine learning for that. And so from that, I'll just read through these for you. Our conclusions. I think the most exciting thing is we are able to run very large ensembles of global CLM, which creates a framework for a lot of interesting science. Our one at a time ensemble is available on Glade. A lot of, I hope people are interested in analyzing that. We have an analysis template available on GitHub, and eventually I'll try and migrate the data set itself onto the cloud. Just as an advertisement, our PPE working group meets about approximately monthly. Our next meeting is February 17th. And please email Dave if you want to join the list. And then in terms of what I was referencing earlier, if you're interested, and I'll send this around to the PPE group, but I've put that sort of list of 50 parameters online and would love any input on that. So this is just a link to a Google spreadsheet of those 50 parameters and a place to comment whether you think, and I have one sheet that's parameters we are including and one sheet parameters that we aren't including. So comments would be like, I can't believe this parameter didn't make the cut, that sort of thing. But with that, I would be interested in any questions or comments.
Thanks, Daniel. It's really interesting to hear more about the PPE and all the great work that's been done and all the resources that are available for the community. We can open up the floor to questions either specifically for Daniel, or this is also the time for the full discussion in general. And so we can revisit questions from other talks as well. So yeah, if anybody has a question, either feel free to enter it into the chat or raise your hand and we can take them. Looks like Will has a question.
Maybe just to get us started, Daniel, there's a ton of speculation in the chat about what that one parameter was that affected the response to future climate, but not present climate. And I'm wondering if you could dispel the myths.
Yeah, I don't know if you can summarize the chat, but I know exactly what parameter it is. It's a TPU acclimation parameter that we added in. I guess I moved too fast.
All experts did not get that.
But TPU is the triose phosphate limitation simulation. There's been a lot of discussion as to whether or not we should actually remove that from the photosynthesis code. So It's interesting to see it has a large effect. Doesn't surprise me that it has a large effect in the future and not at present day. Jackie.
Thanks, Daniel. That was really exciting. I haven't been able to go to a lot of the PPE meetings, so that's really awesome. I was struck by the transition to doing these global or the regional calibrations, because that's kind of a similar approach that we've had in mind for fates. You know, because so much of these competitive dynamics, like calibrating it globally, you can run into these issues. And so we're thinking of a similar motivation on the fate side of things.
Yeah, exactly. And for us, I don't know about you guys, but the only lever we really have on that is PFT parameters. And we're just trying to figure out how to, you know, take best advantage of that. So yeah, hopefully some of our, you know, some of what we learned can apply for you guys too.
Sanjeev has a question.
So Daniel, thank you. This is lots of work. Like every time I try to gather the courage to kind of start looking into, and every time I fail. So yeah, it's a lot of work, and I don't know how you kind of keep the things in your head. So yeah, I'll look into your Jupyter Hub tool. Like one of my specific question was, you have generated 210 ensemble. So, and you have like a 400 of that ensemble. How that ensemble is spread in your experiment compare with now we have the 100-member ensemble CSM2LE. So what is the role of climate forcing versus, or the internal variability, whatever you call there, versus this parameter uncertainty, at least in this known world?
Yeah, that's an interesting question. I definitely haven't looked at it. But yeah, we definitely are looking at one kind of realization of historical climate and how our parameters affect that. So I think that would be a great thing to look at for anything in terms of, yeah, especially for something like variability. I feel like looking at parameter effect versus ensemble effect would be interesting.
Okay, thank you.
Yeah.
Just wanted to note in the chat that Rosie said +1 for data set on the cloud. That's possible, and Dave responded that they plan to put the data set into the LEAP Pangeo in the cloud. Polly.
Daniel, that's awesome work. Thanks so much for sharing this. I just had a question about the Latin hypercube sampling. And can you enforce correlations among parameters within that sampling, or is it absent correlations?
You could. We have maybe like in our top 50 list, we have one parameter that we wanted to, one set of parameters that we're enforcing correlation. And we were doing just a deterministic correlation, so like an exact correlation, which is really easy to do with the Latin hypercube. So it's not like if you had two parameters in some bivariate probability distribution, we're not kind of selecting from that randomly, but we're saying, you know, it's I forget what the parameters are, but it's like, make sure you make all 6 of these parameters high at once and all 6 low at once. So with the Latin hypercube, all we're doing with the Latin hypercube is generating a number from 0 to 1 and then sampling within the parameter range. So like 0.5 would be at the center of the parameter range. So what we're doing is we're taking that 0.5 and applying it to 6 parameters at once instead of creating a separate random number for all 6 parameters. So that type of thing is very easy to manage in the Latin hypercube environment. In terms of doing like bivariate probability distribution stuff, that would be trickier, but I'm sure someone's figured it out.
I was thinking for the PFT parameters, especially with fates, keeping those correlations, you know, cross parameter correlations and then cross PFT relative differences is super important. And so if there's a way to build that in, like I haven't used the Latin hypercube, I've used different methods for doing that, but
yeah,
it would be cool to be able to do that, to make it, you know, bring this to the fates parameter world as well.
Right. Yeah, like I said, I think if you're willing to have them kind of exactly correlated with each other, it would be pretty easy. If you want them to be like, you know, softly correlated with each other, I think that would be more challenging.
Yeah, thanks.
Well,
I know we started having this discussion in a recent PPE meeting, but I guess I wonder if it's worth bringing it up again here, mostly because Dave mentioned in the chat that it's worth that more than one perturbation is needed for the Latin hypercube, and including soil texture as well is probably warranted. And I'm curious, like, you know, of all the data sets that were on that list that Dave shared yesterday, soil properties are one that we know we're going to change and update to something newer. And those were supposed to have come in a few weeks to months ago, and we're still waiting for them. But I guess I wonder if it's, you know, since we know we're updating data sets and some of those might be happening soon, is it worth waiting to run some of these, the Latin hypercube, until we have that new data set to be working with, if part of the idea is to kind of circle back around and inform the parameterization of CTSM6 with this one?
I'll let Dave chime in too, but I personally don't think so. I don't think it's worth waiting. We're already kind of using CLM5, or right. I don't know exactly where we branched from, but we know that this isn't the model that's going to go into production for the next thing. And I think we're mainly trying to learn here. Like take a given model at a given point in time, you know, how good can we do on calibration, et cetera. And then the whole idea here is that it's a repeatable workflow that's like actually relatively easy to run. And so then you would just rerun. That's part of why we only shot for 1 million core hours for the Latin hypercube, because that's kind of something that we can do 4 or 5 or 6 times without kind of worrying too much about blowing the allocation. But yeah, Dave, go ahead.
Oh, I just agree. I think we try now. It could take us a long time to get it to really work. And so, yeah, repeatable once we get the final version. And hopefully, you know, everything's so smooth with what Daniel and Katie have been working on that we should be able to repeat it. You know, we got to think about the timing, but within a couple of months, I think, or shorter, you know, when we need to repeat it.
Yeah, I wanted to, I guess, bring the conversation back, because this is meant to be a discussion for the whole session. So I wanted to just connect back to some of the talks as well. I know that there was some conversation that we had to cut off about the canopy leaf temperature conversation, and thinking about scaling through that. There's also some conversation in the chat about the adding a planetary boundary layer to single column CLM, which might be challenging. And, you know, this parameter sensitivity work also connects back to Claire's talk, to highlighting that these parameters and the parameter sensitivity will have climate impacts. So those are some potential points for conversation. I guess, you know, I could just start by asking, based on Claire's talk and the work that Daniel just presented on the PPE, I'm curious, you know, will we want to start selecting some high sensitivity parameters to look at in the coupled modeling framework? And could the like a PBL single column model or maybe SCAM be useful here in trying to understand some of those impacts? Dave.
Yeah, so actually what hasn't come up in the chat yet is that Isla has run a PPE at a single column site, looking at a different problem, and that seems to be working. So I think we've already established that it's possible. I mean, we still don't know how much information we can get from it. That's still TBD. And I think the other thing to point out in terms of like, do you need a PBL added on top of CLM versus the SCAM? I mean, maybe Meg can give us some information here, but there's different ways to constrain the SCAM, and you can sort of weight the constraints to be like constraining the upper atmosphere very strongly, but then leave the PBL pretty freely running. And so that may be kind of similar to just adding a PBL on top of CLM. And so I think we could at least explore that. I think adding all the infrastructure to add just a PBL on top of CLM would probably be, that'd be a lot of work.
Meg.
Yeah, I'll just chime in and build off of what Dave said. So with SCAM, what we figured out is that it is important to constrain the atmosphere, but you can do that really lightly. So SCAM kind of goes a little bit off the rails if you just let it decide what to do with temperatures and throughout the whole atmosphere. But you can, just constrain it with a really long time period, a month down to like 850 hectopascals. And you can let the PBL just evolve as it wants. So I think it's a really useful tool for land atmospheric coupling. And you can get some really cool results, I think.
That sounds really promising. Really interesting tool.
Well, the reason we can start using SCAM more readily now is that they've resolved some issues. John Truesdale in the CAM group, software engineers, resolved some issues with initializing with a land initialization file, which was not available up until very recently. And so it made it, you had to go from cold start, or you couldn't do resubmit, and a bunch of reasons why it wasn't really that useful for us to do land atmosphere interactions. But those issues have all been resolved. So it does make it a much more useful tool.
Absolutely. One other, it sounds like Sanjeev would be interested in using that in a simple framework. And so I guess I'm wondering, Meg, have you worked with Brian Dobbins at all to get the SCAM into the containerized system for CESM lab? Or is that something that would be of interest?
Yeah, that's a good question. I haven't worked with Brian on that. I think, so the way that SCAM runs, you need sort of like an atmospheric forcing file with some hourly specific data. And so I'm just not sure exactly which locations would have that. But I know there's, preset options in SCAM for different locations. And so if you're interested in like the Arm Southern Great Plains site, it's a real easy one to just run out of the box. And I think we could do that in containerized versions. Yeah.
I think you can get it from all the required forcing files from a reanalysis. So I think to the extent that that's a reasonable application, you could go to all the neon sites and pull out the nearest grid point, and won't be exact, but I think analysis. But that's something we need to talk to the camp group a bit more about.
Yeah, and Eric points out that SCAM is a standard option as part of CESM, and so maybe it already is in the CESM lab container framework. I'll note just with our work with the neon simulation tool in the container system, one of the biggest problems with running on your laptop is the size of the download files. So if you don't have it set up for specific points, it can take a really, really long time to download. And so some of these tools are potentially better used and developed in the cloud, where people can still access a sort of a containerized system, but then some of the data files and computing can be done in the cloud. So maybe that's an option that we should continue to consider as well. I see that Sanjeev says that he agrees that atmospheric forcing can be used for reanalysis. Gordon has his hand up.
Yeah, Meg, this is more of a question for you, I think, but isn't it, there's this, is it the Southern Atmosphere Oxidant or Southern Oxidant Atmosphere Oxidant study or something like that? Yeah, is that a case study that we can, with SCAM, that we can actually sort of start working with? You know, Ned has mentioned this to me several times that, you know, in terms of perhaps of coupling the multi-layer canopy into CLM and getting it to feedback with CAM. That's a case study that maybe is a way that we people in the land working group can start working with SCAM, because it's all set up. I don't know too much about that. I don't know if you could say anything, if you've been working with that, or if you could say anything about it.
Yeah, that's a good question. I think that kind of IOP is something that John and Rich have been actively developing. You know, I've seen it be mentioned a couple times, but I don't know exactly the status of where they are with it. But John Truesdale would probably be the person to get in touch with. I know he's been making sure SCAM can run with that. So he'd probably have insight on how well that's working right now with an active land model. Yeah.
Okay, the thing, and Sanjay, I think that was for a pine forest in Alabama, I think is what the case study is about. I can't remember all the details, but I'm pretty sure it's a pine forest in Alabama for a short period. Measurements were made for a short period of time.
Yeah. Yeah, thank you, Gordon. I'll look into it if if the study is available. Top of head, I'm not aware of.
Yeah, I see Katie has her hand up.
Well, I thought I would try and start to answer part of Daniel's question in the chat, which Sanjeev also sort of brought up earlier, of how the machine learning community can help improve our calibration efforts. And I think this is a really open-ended question, but there's some things we've been thinking about, especially through the NSF LEAP project. And one is just the kind of a straightforward example of using machine learning to build emulators of the PPE output, and then use those emulators to improve the computational efficiency of parameter estimation. Yifan talked about this. Perhaps others are also using emulators in this community. But it would be interesting to think about other ways we can bring in machine learning, which is, it's just a tool. It's just another tool in the toolbox that's getting a lot of attention right now. But for example, doing the parameter selection, sampling the parameter space, disentangling structural uncertainty from parametric uncertainty are all kind of, I think, open-ended areas where we might be able to think about bringing in machine learning. So I'll just leave it at that for now.
Those sound like exciting opportunities for, you know, thinking about some machine learning applications. Seems like our questions are slowing down, and I know that it's been a long week. Let's see, Ben, through Rosie's account. Ben, did you want to add anything? I just read.
Oh yeah, no, I'm just thinking about the boundary conditions for SCAM, and like, you know, there's presumably quite a nice potential for using existing. Yeah, I mean, you can store SCAM boundary conditions from an existing CAM simulation, right? So looking at some future simulations, storing those boundary conditions, then looking at the CLM parameter sensitivity of point sites from in those idealized futures. You know, you could do some neat stuff with that. Especially looking at land use, local biophysical effects, that kind of thing. It's, there's some scope there. If the machinery is there, then that would be a fairly easy thing to do.
Right. And I see Matt V has a suggestion for Daniel with regards to the Latin hypercube part of the PPE. You might also want to look into Sobol indices. There's a link to a paper. I guess last call for other questions or comments. Like I said, I know it's been a long week. I imagine everybody's tired, but it's been a really great set of talks. It looks like Charlie has a question. Daniel, are the parameter correlations coming from something like try?
No, that would be nice. And I think if we had a smaller experiment, we might try something like that. But with 200 parameters, it was a little challenging to do that. There was just like, I would say like 4 or 5 different parameter sets that we just knew couldn't be perturbed independent of each other. And so we just kind of used expert judgment to require that they move together. So it's the type of thing that honestly should probably be more in the source code. And it should just be one parameter controlling these 6 numerical values. It's like that kind of strong a connection. But yeah, using something in try would be kind of interesting. Because we know there are certain areas of parameter space where you think of 2 parameters that just like don't actually exist in nature, etc.
Thank you. Joshua has a question for Lei. I know that Lei had to leave, and so I was wondering if maybe Keith could comment. Cities have very different amounts of water than surrounding lands. Does the urban model represent open water within cities? It appears that the model falls a little short in the simulation of latent heat flux.
Yeah, it doesn't have open water within cities. There's pervious surface, but it's like a kind of a bulk approach to represent evaporation. And so Lei's project, one thing they're going to work on is perhaps putting like a simple vegetation model within the canyon to improve the latent heat flux. But also depends on what you call an urban area also, what your boundaries are and what falls within it. And you might be able to, represent these types of things with a tiling approach perhaps, and combine fluxes from the urban model with fluxes from the open water and get reasonable results for things like that. So.
Thanks, Keith. That's informative. Okay, well, we have just 2 minutes left, so I'll hand it back over to Will for any final comments. Before I do, I just wanted to say thank you to Will. This is a huge effort to put together this meeting, so thanks for all of your hard work in that, and also thank you to Elizabeth for all of your help. So, and Will, if you have any final comments.
Sure. Yeah, I guess I'm, as always, humbled by all the work that everyone's doing and appreciate the energy that went into presenting these talks and the discussion that followed. And as always, as much as you can keep us informed with what you're doing and let us figure out ways to help make connections and help you out with the science that you're trying to do. I think that's one of our roles that I think improves both working groups, both the land model and biogeochemistry working groups. So thanks again to Elizabeth, and thank you guys for joining in. Look forward to seeing you in person before too long.
Next year for sure.
Thanks, everyone.
Yep.
Thanks, Will.
Thanks.
Bye.
Okay. Nice job, Will. Great meeting.
Good to see you, Sam.
Okay, Sam.
Say bye-bye, Sam.
Bye-bye.